Welcome, friends. You are here in a quiet room, listening in the gentlest part of the evening. In this series, you and I travel as calm observers, drifting beside real mysteries and the instruments that study them. We let science set the bones of the story, and we let imagination breathe, but only as far as the physics will allow. So, before our journey begins, take a moment to like the video and subscribe, but only if you feel a genuine connection to the mysteries we explore here. If you're comfortable, share your location and your local time in the comments so we can imagine this same sky stitched across many places at once. Now, dim the lights, let the world outside fade away, and let's drift into the cosmos together. We begin, as always, with a soft echo. The room is dim, the screen is a small moon, and somewhere far away, a faint traveler is curling a pale veil into space. In the next few minutes, we will look at a timing puzzle that has bothered planetary scientists for decades. And we will meet a messenger whose arrival makes that puzzle feel more urgent and perhaps more solvable. Picture a newborn star, wrapped in a thin, silver ring of gas and dust that shines like frost under a morning sun. Here is the problem, stated simply. Giant planets should not be easy to build. The gas they need is present for only a short time, while the solid cores that capture that gas often take longer to grow than the gas lasts. The universe appears to play a game of musical chairs, with the chairs removed early. And yet, when we look around, gas giants are common enough that the old models feel rushed and out of breath. Let us set the clock with a handful of rounded numbers, then move on. The dusty gas disk around a young star tends to thin out in roughly 3 million years, sometimes closer to 5. To become a gas giant, a planet usually needs a solid heart of about 10 Earth masses so that gas can fall in fast. In classical planetesimal growth, stacking rocks to build that heart can take tens of millions of years in many parts of a disk. Newer ideas like pebble accretion can shorten that to roughly 1 million years under favorable conditions, but those conditions are not guaranteed. Meanwhile, the gas keeps escaping. In short, the hourglass in the nursery runs out quickly, while the core often lingers over its homework. This is our first hard fact. Disks lose their gas on a timescale of only a few million years. This is our second hard fact. Many growth pathways for a solid core require comparable or longer timescales, especially far from the star, where giants often live. The mismatch is the heart of the paradox. If the recipe takes longer than the oven stays warm, how do we keep baking these large worlds so often? You can feel the solutions people have proposed tugging at different parts of the disk. Perhaps the core forms closer in where the material is dense, then migrates outward. Perhaps the disk itself helps by funneling pebbles along pressure ridges so the core eats more efficiently. Perhaps the seeds form early in small clusters that fuse and feed. Each option eases the clock, but none of them alone closes it for every case we see. The field has become a map of clever adjustments, and still the timing feels tight. Now imagine a different beginning, one that shifts the starting line. Instead of a world that grows from local dust, picture a ready-made core wandering in from interstellar space, a compact package already heavy enough to invite gas. It enters a young disk, meets a headwind of gas that slows it just enough, surrenders to gravity, and then sinks into the plane like a pearl settling to the bottom of a bowl. Gas wraps it. Pebbles stream toward it. The timeline collapses. The music keeps playing, and the chair is still there. This is grounded speculation, not a leap. If such wanderers exist in large numbers, and if capture is not too rare, then some fraction of giant planets could start this way. The benefit is not magic. It is bookkeeping. You begin the race with half the distance already run. The universe loves shortcuts when they are allowed, and this one uses only the ingredients we already believe in. Solids, gas, gravity, and time. If that idea sounds like a story, with the seeds already planted, keep the image, but set aside the metaphor. What matters is that a captured core would erase the slowest step. It would also carry the chemical memory of a different star, a signature that might linger in the final planet. That detail will matter later when we talk about fingerprints. For now, return to the disk and let it be a place of gentle traffic. Dust settles. Pebbles drift inward like tiny rafts. Vortices herd material into islands. A passing core nudges the gas and leaves a wake. Even without visitors, the system is not still. With a visitor, the choreography gains a sharper rhythm. The ready-made body eats quickly and tips into runaway gas capture, while the disk is still rich. The clock becomes a companion instead of an opponent. You may ask, why assume such visitors exist at all? We have a calm reason to keep the question open. Our solar system has already hosted 2 confirmed interstellar objects, and now a third has arrived. The first was light and odd. The second looked like a more familiar comet, and the third is active and chemically rich. If 3 have come within a few years of each other, how many pass by without being seen? And how many pass through younger systems where the gas is thick and the capture easier? Numbers alone do not prove the pathway, but they lift the idea from fantasy into possibility. A single, vivid image to hold. Think of a glass blower turning a rod through a thin breath of fire. The rod is the visitor. The flame is the gas in the disk. And the turning slows the rod just enough for the glass to gather. The shape that follows is not an accident. It is a consequence of contact. There is a psychological comfort in this picture. The timeline problem becomes less of a frantic race and more of a rendezvous. A core doesn't have to make itself from crumbs under a strict deadline. It only needs to arrive while the gas is still generous. That is easier to imagine and perhaps easier to test, which brings us to the messenger now traveling under our sun. The object we call 3I, discovered recently by skywatchers who scan for moving points, is a stranger bearing a particular set of traits. It is active. It sheds a veil of carbon dioxide and water. Its dust behaves like it remembers a different nursery. We will lean on it in this story, not as proof, but as a case study. If a seed exists, here is a place to practice seeing one. Before we meet that visitor in detail, hold the structure of what comes next. We have named the problem We have introduced a pathway that could ease it. We have a real object to examine against that pathway. In the following chapter, we put the traveler on the stage and mark its orbit through our system. As we do, keep one question nearby, light and open, to carry you into sleep if you wish. What if the start of a world is not local at all, but a quiet gift from somewhere else, arriving right on time, like a pocket, warm and sure, a quiet window, a quieter sky, and the steady habit of watching. Night after night, the surveys sweep, and then a small point moves in a way that does not fit the usual family of paths. The alert came from a modest but tireless network, the Asteroid Terrestrial Impact Last Alert System. A track of positions became a curve, and the curve became an orbit that refused to close. The numbers said what the eyes already suspected. This object was not bound to our sun. It came from between the stars, and it would leave for them again. Give the visitor its name. 3I, the third interstellar object we have recognized, catalogued by the survey that first noticed its odd flight. The name also carries Atlas, a reminder of the vigilant instruments that caught it early. A small body, outwardly simple, inwardly interesting, threading the inner system on a one-time pass. Two steady facts set the stage. First, the orbit is hyperbolic, which means the eccentricity is greater than 1, and the object is not captured by the sun. Second, the speed at great distance from the sun exceeds the escape speed of our system, so even if nothing else happened, it would come and go with only a faint tug. Those are the clean signs of an interstellar origin. No flourish is needed. A path that does not loop, a speed that does not fade to bound. And the case is made. It helps to recall the short history of this category. The first visitor, 1I, was faint, fast, and strange. It showed no coma that we could see, and it nudged itself in a way that sparked debate. The second, 2I, was recognizably cometary, a more familiar sort of traveler that still came from far away. Our third visitor arrives with a brighter personality. It carries a living veil, gives off a well-formed tail, and responds to sunlight with a chemistry that will occupy several chapters of the story. 3 data points are not a population, but they begin to outline a landscape. Look at it for a moment, the way observers do. On images taken minutes apart, the dot slides against a sprinkled field of stars. Stack the frames, and a thin tail appears. Sunward jets pulse, and the scene turns from geometry into weather. The coma is not a cloud in the usual sense, but a fountain of gas and dust that escapes as heat loosens the grip of ice. Seen at very high magnification, the dust is a slow snow of tiny grains, falling outward instead of down. Keep the technical details compact, then return to the quiet. The eccentricity is greater than 1. The excess speed at infinity is measured in tens of kilometers per second. The path dives toward the inner system, brushes near the orbit of Mars in early October, and then swings past the sun later in the month before fading. Follow-up observations, in visible and infrared light, have already confirmed sustained activity. Teams on the ground and in orbit will sample the light and pull out the fingerprints of the gases and solids. That is enough scaffolding for now. Here, is the vivid image to carry. Imagine a dark seed crossing a field of pale wind. Sunlight is the wind, gentle at first, then stronger, and the seed exposes a bright breath that trails behind it like silk drawn through water. The breath is not decoration. It is evidence of what the seed holds inside and how it responds when warmed. Our two hard facts for this chapter are simple. The object is interstellar, demonstrated by its open orbit and excess speed. The object is active, demonstrated by its coma and dust tail, seen by independent telescopes. Those facts do not imply purpose, and we will not assign any. They do, however, make the visitor a better laboratory, because composition in a living coma is easier to sample than composition locked in a bare rock. There is a grounded speculation that naturally follows. If an interstellar object can remain intact long enough to cross a star system, and if it is rich in easily sublimated ices that awaken at moderate sunlight, then a young system with a gas disk would meet it as a body with surface drag and a large cross-section for interaction. Gas would slow it. Gravity would do the rest. A traveler like this could be captured under the right conditions, and once captured, it could become the nucleus of something larger. This is not a claim, only a conditional path, but it is a path drawn with tools already on the table. The observer's job now is to set aside hurry and let the sky do what it does. The orbit will carry 3I through a geometry that gives us several vantage points. When the object passes near the orbit of Mars, spacecraft at Mars can watch from a privileged angle. When it bends around the sun, telescopes sensitive to heat can trace deeper layers as fresh vents awaken. The weeks between those two moments will be a natural experiment that only a wandering body can provide. If you enjoy patterns, sketch a small history of attention. In less than a decade, we have moved from never having seen a confirmed interstellar object to seeing 3. The first forced a conversation about how light bodies move when pushed by sunlight. The second reminded us that the most distant comets can still look familiar when viewed up close. The third arrives at a time when our instruments can parse chemistry with unusual precision. Each one landed in a different part of our capability curve. That is lucky. It is also a sign that surveys are finally fishing at the right depth. A brief, dry joke is allowed in a sleepy lab voice. The universe appears to be sending us a syllabus. Week 1 was kinematics. Week 2 was cometary physics. And week 3 is chemistry and dust. We will take notes. You may feel a tug toward a broader story. Where did 3I begin? Did it form in a calm outer belt around a small star, or in a busy nursery where larger bodies were often thrown out? Did it carry the metal ratios of an older part of our galaxy? The honest answer is that those questions are too large for a single pass and too delicate for a firm label. The better approach is to build a profile from what the light reveals and then compare that profile to models of formation environments. That comparison can hint at an origin without pretending to solve it. What matters for our journey is that 3I is a messenger with a readable envelope. The gas in its coma will tell us about volatiles that release at different temperatures. The dust will tell us about grain size, structure, and how light scatters from material that formed under a different star. The way activity rises and fades with distance will tell us about layers and crusts, about how deep the fresh ices sit, and whether the body is crusted over or easily vented. Each of those details supports or challenges the idea that such a traveler could act as a seed. Hold a quiet question as we pause. If a young disk had met this traveler many millions of years ago, would it have kept it? And if it had kept it, what kind of world would have grown around it? In the next chapter, we will open the envelope and read the first lines. We will look at the composition of the coma, which leans toward carbon dioxide and water in a ratio that is not typical of many comets nearby. And we will consider what such a mixture implies for ignition, stability, and travel. For now, let the image of a dark seed and a pale wind rest beside you as you breathe. The sky will keep its appointment. We will be ready when the light returns, like a pocket, warm and sure. A low hum of night and a clean line of starlight through the window. The visitor turns a little closer to the sun, and the thin breath around it brightens like frost warmed by a quiet lamp. What first drew attention was not the path, but the envelope of gas itself. Instead of a bare stone or a reluctant smear, the object lifted a clear, readable coma. Observers pointed spectrographs and found familiar tones in the light. Carbon dioxide spoke in the infrared. Water answered at shorter infrared wavelengths. The scene shifted from orbit mechanics to chemistry, which is where stories of origin often begin. Hold a compact cluster of technical notes. Then we will go back to calm images. Carbon dioxide has a strong band near 4.3 microns. Water has a broad set near 2.7 microns. The violet CN band sits near 0.39 microns. These features are standard candles in comet work. Their strengths, ratios, and how they rise with sunlight tell us which ices are shallow, which are locked below a crust, and how heat moves through the body. Carbon dioxide can sublimate at lower temperatures than water, so a traveler rich in CO2 can wake farther from the sun. Water usually waits for a warmer stage, then joins. 2 hard facts for our table. First, this interstellar visitor is active with a sustained coma and tail seen by multiple teams. Second, spectroscopy detects carbon dioxide along with water, making the chemistry accessible during a single pass. Those facts are enough to justify a careful look at the balance between the two, without assigning more than the data can carry. Return to the image. Picture a dark core with a thin, fragile rind that cracks under gentle warmth. Through those seams, carbon dioxide escapes first, fast enough to lift grains and throw sunlight into a halo. Later, when the skin warms and deeper pockets loosen, water joins the breath and thickens the veil. The coma is not decoration. It is a moving ledger of what the body holds near the surface and how it is layered. Why does a CO2 forward coma matter for our question about seeds? Because it broadens the temperatures under which a small body can stay active. A seed that can ignite with carbon dioxide far from a star, then continue with water when closer, can operate across many environments. on a long interstellar cruise. That mix also helps retain shape. Carbon dioxide can seal under refreeze, building temporary crusts. Water can knit grains. Both can preserve interior pockets until a new star's light arrives. Dust adds a second, subtler calling card. Light scattered by the coma is slightly polarized, and that polarization shifts with viewing angle. The pattern depends on grain size and structure. Fluffy aggregates scatter differently than compact fragments. Sooty organics behave differently than pure silicates. Early hints suggest a mixture that is not a perfect match to many comets catalogued here at home. That does not prove a separate origin, but it nudges us to treat the dust as evidence, not background. Keep a brief, technical breath for the dust. The negative polarization branch at small phase angles. The slope toward positive polarization as the angle widens, and the absolute levels can be compared against models of fluffy clusters and compact grains. If the grains are porous, they tend to polarize light more strongly. If they are compact, the effect softens. This is not trivia. Grain structure tells us about the environment where those grains were built and processed. A quiet nursery makes a different kind of dust than a crowded one. Now, a grounded speculation. If an object formed in a cold outer belt, around another star, away from violent heating, it could preserve a surface with easily awakened CO2 and a population of fragile grains. That kind of surface would flare into activity early, carry a distinct dust signature, and respond to sunlight in a way that makes capture more plausible in a young gas disk. None of this requires exotic physics. It asks only that the traveler's pantry was stocked in a different kitchen and kept sealed by time. There is a practical advantage for would-be seeds hidden in this chemistry. Carbon dioxide jets can produce gentle, sustained thrusts that keep vents open without shredding the body. Water vents, once active, can carry larger grains and build a denser, more collisional coma. Together, they create a two-stage engine. The first stage wakes the surface and lifts fines. The second stage deepens the flow and entrains larger particles that add mass to any surrounding medium. In a young disk, that extra cross-section would matter. Gas drag grows with area. A lively envelope bites harder into the headwind and bleeds off speed more efficiently. You may notice a quiet pattern in our first 3 chapters. We start with a timing problem, meet a traveler, and now read the traveler's envelope for clues about how easily a seed could interact with its environment. Each part is modest. Together, they suggest that composition is not merely a label, it is a function. The same mix that makes early activity possible also makes aero capture in a gas-rich nursery more likely, and it makes rapid early accretion more efficient by dragging grains inward. There is, of course, restraint. Ratios of gases change with distance from the sun and from one observation to the next. Surfaces evolve across a single apparition. Dust properties can look different simply because our viewing angle changes. We do not overread a single night or a single instrument. Instead, we watch the curve of activity rise and fall. Compare the same bands over several weeks and let the body tell us about its own layers through repetition. A vivid image to keep by you as you breathe. Think of an inkstone dipped in cool water. The first narrow plumes of ink moving out like silk. A warmer pour follows, and the water turns richer as deeper pigment escapes. You do not need to see the stone's interior to know that the first wash came from a thin outer layer, and the second came from within. The coma is the same kind of art. It is the way the body reveals depth without cutting. Let the second hard fact settle beside the first. Jets are not smooth. They pulse with rotation. As the nucleus turns, vents aim and then turn away, and production rates breathe in patterns with the spin period. When we see a repeating rhythm in gas output and dust brightness, we can estimate that period and map active regions. Rotation matters because the location of those regions hints at crust strength, layering, and thermal history. Those are the quiet, mechanical details that any seed hypothesis must respect. What remains open, gently, is how unique this balance is. Do most interstellar bodies present similar CO2 forward wakes? Are their dust grains consistently more fragile or more compact than our long-period comets? Does the mix we see here point to an origin in a colder, older part of the galaxy, or simply to a local patch in a distant disk that happened to favor carbon dioxide and water in this ratio? The question is not a cliff edge. It is an invitation to keep looking. As the visitor moves toward its appointment near the orbit of Mars, instruments will compare these bands again from a new geometry. If the ratio stays steady, that suggests thick reservoirs. If they change quickly, that suggests a patchwork of seams and crusts. Either way, the envelope will keep writing its small, legible notes. We will follow those notes in the next chapter, placing 3I beside its two predecessors to see what changes from one visitor to the next and what stays the same. For now, let the calling card be simple and calm. Carbon dioxide wakes first. Water joins later. Dust carries a memory, and the whole breath makes the traveler easier to see, easier to slow, and easier to imagine as the heart of something larger, like a pocket, warm and sure. Curtains breathe once in the night air. The screen is a small square of quiet light. We are close enough now to compare three travelers with one steady gaze. Begin with the first letter in this new alphabet. The object named 1I arrived as a shard that refused to carry the usual mist. It showed no readable coma in the images taken then. Its brightness rose and fell as it spun, hinting at a stretched or flattened shape. Later, the path required a small, extra push, not fully explained by gravity alone. Some argued for gentle outgassing too fine to see. Others tested light pressure, surface textures, and shapes. In the end, the lesson was simple. Interstellar space can send us bodies built in unfamiliar ways, and not all of them carry the easy chemistry of a classic comet. The second letter, 2I, felt more like a note we already knew how to sing. It wore a clear coma and a clean tail. Spectra found common comet gases. Telescopes tracked dust lifted in steady flow. It was interstellar by orbit, but in behavior, It resembled comets that orbit our sun. That did not make it unimportant. A familiar look from a foreign body helps anchor the category. It proved that at least some interstellar visitors carry abundant volatiles that wake when warmed, and that their dust can behave in ways our models understand. Our third letter, 3I, brings the two moods together. It is active like 2I, but the balance of its breath feels different. Carbon dioxide speaks early and clearly. Water joins and thickens the veil. The dust does not scatter light in exactly the same way as many comets we have catalogued here. This is not proof of anything by itself. It is a profile. And a profile is enough to ask better questions. Hold a vivid image for orientation before we stack facts. Imagine 3 stones skipping across a pond at night, each with a small light inside. The first throws a light that flickers strangely and leaves almost no spray. The second gives a familiar glitter of droplets. The third throws a wide, steady fan, and the spray glows with a cooler hue. Same pond, same hand, different stones. The differences are not drama. They are information. Now, the compact, technical moment. 2 hard facts for our page. First, all 3 objects follow hyperbolic paths with speeds that confirm their interstellar origin. Second, only the latter 2 display a sustained coma that allows direct chemical sampling. Those facts shape how we can use them. With 1 eye, we map shape and motion and infer. With 2I and 3I, we also read chemistry as it unfolds in sunlight. Place 3 beside the others and notice how it helps with our central question. If interstellar bodies can arrive with gas that ignites early, and if that gas can lift fine grains into a wide envelope, then in a young star's disk, the cross-section for drag increases. A larger cross-section means stronger slowing. Stronger slowing means a higher chance of capture. This is a grounded speculation, not an imaginative leap. It simply says that the way a body breathes can change what happens when it meets a gaseous nursery. There is a soft joke in the lab notebook that someone will write later. Our first visitor tested our patience. Our second tested our procedures. Our third is testing our capture math. That is a tidy syllabus, even if the universe never meant to set one. It is helpful to ask what these 3 say about diversity. If 1 eye was likely crusted or depleted at the surface, and 2I was a vigorous fountain of familiar volatiles, and 3I is a fountain with a chemistry that leans toward carbon dioxide early, then the interstellar population is probably broad. A broad population increases the odds that some members are built in ways that favor capture. It also increases the chance that at least a few seeds arrive with the sizes and structures that make rapid growth easy once lodged in a disk. We should also consider the dust. 2I's dust formed a coma with properties many of our models already handle. 3I's dust, by early hints, carries a scattering signature that suggests different grain structures or mixtures. Porous clusters behave differently from compact grains. Organic coatings darken and alter polarization. The interior of a disk, the rate of gentle collisions, and the warmth of occasional heating all mark the grains. If 3 ice grains are especially fragile, then capture in a gas disk could be even more efficient, since fragile aggregates present larger effective area for the same mass. Keep the numbers rounded, then move on. The nuclei in these cases are small, likely between a fraction of a kilometer and a few kilometers for the active ones. Their speeds relative to the Sun are in the range of a few tens of kilometers per second. Their visible comet span thousands of kilometers when active, in a disk that survives for roughly 3 million years. Even a rare encounter rate could matter. You do not need hundreds in one system. A few in the right window would do. There is a practical lesson hidden in the contrast. With 1 eye, we learned not to demand a coma before we accept an interstellar label. With 2 eye, we learned that chemistry can be read cleanly during a single rush through the inner system. With 3 eye, we are learning that some visitors wake in a way that changes the balance of capture physics. Each has carried a different part of the conversation, and each has pushed the field toward a sharper set of tests. What about the fear that we are forcing a pattern onto a small sample? That fear is worth keeping on the desk. 3 points do not make a strong statistic, but the right 3 points can frame sensible hypotheses. Are CO2 forward visitors common? Do they tend to carry dust with higher porosity? Do such properties line up with specific stellar birthplaces? These are not romantic questions. They are lab questions. They ask for more objects and for better light. A small grounded speculation on origin, kept calm and conditional. If 3I formed in a colder, more carbon-rich region around a star with lower metallicity than the Sun, it would be reasonable to see carbon dioxide wake early and to see dust that leans porous. If it bounced around a crowded young system before ejection, it could have lost some of its most volatile layers and kept a mixture that survives long cruises. Nothing extravagant is required. Only time, distance, and the standard processes of a planet-forming disk. Return for a moment to the picture of capture. A body breathes out a soft, persistent envelope. It meets a gas disk that behaves like a broad, slow river. The envelope increases drag. The nucleus loses speed. The path bends from a flyby toward a long loop and then a settled path. Once settled, the same envelope that helped with capture becomes a conveyor of grains. Local material rains in, the core grows. So the chemistry that made the traveler easy to see is the same chemistry that would have made it easy to keep long before any telescope existed. The comparison also suggests what to look for next. Changes in gas ratios with distance can flag layering. Rotation periods inferred from jet pulses can reveal the distribution of vents. Polarization as a function of phase angle can reveal grain structure. If 3I behaves in ways that are consistently distinct from many comets native to our system, then the case that it formed under different conditions grows stronger. That does not prove a seed. It does show that the seed profile is not invented from thin air. Let a single open question close this chapter. When we have a dozen interstellar objects with good chemistry and dust profiles, will we find that 3I sits on a common branch of a family tree? Or is it a quieter outlier that happened to arrive when our instruments were ready? The answer will either build confidence in the seed idea or sharpen it into a narrower claim. Either way, the sky wins. In the next chapter, we gather the clues and ask directly whether the pattern we see is just coincidence or an early outline of a mechanism. For now, the night remains simple. 3 letters, 3 moods, 1 question that will not hurry, like a pocket, warm and sure. The room is a low tide of shadow and soft blue light. A single point in the sky draws a faint scarf behind it. You can almost hear the careful click of instruments turning. What follows is a choice. Do we treat the signals as noise from a long journey, or as hints of a plan the physics can allow? Think of attention as a lens that gathers rather than magnifies. We have a timing puzzle that prefers shortcuts. We have a traveler whose chemistry wakes early and stays readable. We have dust that scatters light in a way that does not match much of our local catalog. Each piece is ordinary on its own. Together, they begin to echo, keep our compact technical cluster in one breath, then return to calm. Protoplanetary gas lasts only a few million years. A solid core of about 10 Earth masses is the gateway to runaway gas capture. Building that core from local rubble can be slow unless conditions are perfect. An interstellar object with a hyperbolic path and a coma rich in carbon dioxide and water has now entered the conversation at the right moment. Here are 2 steady facts to place like markers. First, this visitor is interstellar by orbit and speed. It is not bound to the sun. Second, it is active in a way that makes chemistry measurable during a single pass. A vivid image to hold the argument. Picture a black seed floating through a river of thin air. Where the seed breathes, the river grips. The envelope slows the seed. The path curves. In a young disk, this is not poetry. It is surface area, gas drag, and time. The same envelope that makes the visitor easy to see would make it easier to keep. The word seeded sounds bold, so let us be exact about what is and is not being claimed. No purpose, no design, no guiding hand. Only this grounded speculation. A portion of giant planets might begin with cores that arrive from elsewhere. Those cores would shorten the schedule by removing the slowest stage. They would also carry chemical memories that differ from the local mix. The chemical calling card matters because function rides on it. Carbon dioxide awakens far from the sun and can keep a coma alive at lower heating. Water joins later and thickens the flow. Together, they create a 2-stage engine that increases cross-section and sustains drag. Dust that is fragile and porous does the same. None of this needs special pleading. It is the same mechanics we use for comets, applied to a different starting point. Skeptics ask a healthy question. Are we seeing a pattern, or just choosing to connect scattered points? Selection bias can fool even careful minds. Perhaps we noticed this traveler because it was bright and nearby, and we now risk building an idea around an easy target. The answer is not a declaration. It is a plan. Gather more visitors. Measure the same bands. Compare dust polarization curves. Let statistics decide. A second hard fact points the way. Large surveys are about to multiply our sample. When sky cameras reach deeper and sweep wider, the rate of interstellar discoveries will rise. With dozens of cases, profiles will either cluster or spread. If many objects show similar chemistry and dust, then we have a branch on the family tree. If they scatter everywhere, the seed pathway stays possible, but less common. Consider the old timeline problem again, now lit from the side. If even a small fraction of systems receive a ready-made core, while gas still blankets the disk, then the paradox softens. You do not have to build every giant planet from first pebbles under a strict clock. Some begin closer to the finish line. That alone would help explain why giants show up as often as they do in surveys of exoplanet systems. There is also a quiet prediction hidden in the idea. Planets that form around captured cores would carry traces of a foreign nursery. Isotopic ratios in their atmospheres might differ from local expectations. Elemental abundances might tilt in ways that do not fit the star they orbit. We already look for such mismatches when we study hot giants. The trick is to measure cleanly and to remember that migration can blur the lines. Keep the scene grounded with a modest inventory of what we can test soon. The visitor's rotation period can be read from pulses in jets. The depth of layering can be inferred from how gas ratios change with distance. Dust structure can be teased from polarization as the phase angle shifts. Solid grains lifted by water near the warmest part of the path will say something about cohesion and crust strength. Each piece connects directly to capture physics. If the case turns out to be coincidence, nothing breaks. We will have mapped a unique object and refined our tools for the next one. If the case becomes a pattern, the field gains a new pathway that fits the numbers without forcing them. Either outcome makes the sky larger. That is a sober comfort in a subject that can drift toward big words. A small aside in the tone of the sleepy physicist. The best ideas are often the ones that make multiple complaints go quiet at once. A captured core shortens the clock and offers a reason for certain chemical anomalies. It makes sense of why some giants seem overachievers. One more image. Imagine a loom in a dark room, threads pulled from distant places, crossing under a simple rhythm. The shuttle is the traveler. The fabric is the disk. The pattern that emerges is not magic. It is contact, friction, and time, woven until a world can hold its shape. Leave yourself one gentle question as we pause. If a young disk once kept a traveler like this, what signature would that adoption leave for us to find many years later when the gas is gone and the planet stands alone? We close this opening movement with a soft, open edge. The timing problem taught us to look for shortcuts. A messenger arrived with a readable envelope. The dust spoke in a different voice. None of this proves a seed, yet the idea now has a quiet place at the table. Next, we walk the method, from capture to rapid growth to the fingerprints it should leave, like a pocket, warm and sure. The river of thin air from before is still in your mind. The traveler breathing against it. The pattern just beginning to show on the quiet loom. Now, the view widens. The dots we traced become a method. We turn from coincidences to a proposal that is sober, testable, and a little bit daring because it moves the starting line. Imagine the problem as a locked door and the key already in the room. The door is time. The key is a solid body that arrives with its mass mostly finished. Astrophysicist Suzanne Faltzner gives the key a name we can work with. She calls it an interstellar seed, a visitor that a young disk can keep and grow into a world. Start with the bones of the idea and place them plainly. In a typical system, gas-rich disks fade in roughly 3 million years, sometimes longer, sometimes less. To pull in gas, a forming planet needs a heavy heart, near 10 Earth masses, so the inflow can run away. Building that heart from local rubble is often slow. If the heart comes from elsewhere, the slowest step is skipped. The schedule that used to fail now fits. Here's our compact technical cluster in one breath so we can return to images. Capture can happen when a body meets gas and loses speed through drag, while gravity bends its path. The loss is small per pass, larger if the body is surrounded by a bright envelope that increases area. If the path loops inside the disk, friction finishes what gravity began. The visitor goes from a flyby to a bound orbit. Once bound, local material streams inward and the core grows. Nothing exotic is required. Only gas, mass, and time spent together. You may think of an aircraft making a gentle aerobrake at the edge of an atmosphere, except the craft is a natural stone, and the atmosphere is a young disk spread thin across space. The image holds because both rely on the same physics. Surface area, relative speed, and the density of the medium decide the outcome. 2 hard facts keep the story honest. First, systems form with gas disks that do not last long, so any pathway that shortens the early growth phase gains a clear advantage. Second, interstellar bodies exist, and at least some of them carry active envelopes rich in carbon dioxide and water, which means they present large, effective cross-sections when warmed. These facts are not assumptions. They are measurements that we already use for other arguments. Now, the grounded speculation, spoken calmly. If seed capture is common enough to matter, then some giant planets should carry fingerprints of a foreign nursery. Their atmospheres might show elemental mixes or isotopic tilts that hint at a different star. Their orbits could be shaped by where the capture settled them in the disk before migration took over. Such marks would not be neon signs. They would be the kind of quiet mismatches that statistics can catch. Return to a vivid scene, so the idea lives in your hands and eyes. Picture a smooth stone slipping into a broad, slow river at dusk. It enters at a shallow angle. The water grips the edges first, then the whole body. The wake softens. The curve becomes a circle. A little silt gathers behind it. Over time, a bar forms, then an island, then a small shape that can keep its outline against the current. The stone is the seed. The river is the gas. The island is a core that has begun to feed. There is an elegance here that is easy to miss if we run too fast. The same chemistry that makes a traveler bright also makes it easy to slow. A carbon dioxide forward coma wakes early and widens. Water thickens the cloud near the star. Dust carried outward increases drag further. The envelope that lets us read the object with telescopes is the envelope that would let a disk keep it. Function and observation are not separate. They are two sides of the same process. A brief, dry smile can live in the margins. We often say that nature recycles. Here, the universe recycles cores. Some are thrown out of their birthplaces. A few find new homes. If true, it is a tidy solution to a messy clock. Skepticism is part of the craft, so we give it time at the table. How many seeds would a typical disk see while the gas still lasts? How efficient is capture at real speeds and densities? Do the seeds survive long enough to arrive with their strength intact? These are not vague doubts. They are questions we can put numbers to, and models already exist that make the first answers. Early work suggests that capture is unlikely in a single skim, but becomes plausible when a body loops and grazes the disk multiple times. The odds climb when the object is small enough to present area without too much inertia and large enough to survive venting. That is the practical Goldilocks zone. There is also the matter of chemistry as a carrier. Seeds that formed in another system could deliver materials that our local disk lacked at that place an hour. They could bring noble gases into an atmosphere early, or tip the balance of refractories in a young core. Even if the final planet ends up far from where the capture began, it may keep a trace of that first adoption. Let us return to the listener's bench and look at the flow of tests that follow from this idea. If seeds help birth giants, some worlds should show atmospheric blends that do not fit their stars. Measurements in the infrared can check that. If capture prefers certain sizes, our census of interstellar bodies should show a sweet spot in diameter where activity and survival overlap. Surveys can check that too. If gas drag is the quiet engine of capture, then objects with broader envelopes should be overrepresented among successful seeds. The current visitor gives us a chance to watch that envelope rise and fall as it moves through different light. One more image, the softest of the set. Think of a library with books bound in different kinds of paper. Some that came from nearby mills, and some that came from far away. The ink is the star's chemistry. The paper is the seeds. When you read a planet's atmosphere, you read both at once. Most books match their shelves. A few carry a foreign paper that can be traced to a distant press. It takes practice to feel the difference with your fingers. The narrative now commits to a path. We will use the seed idea as a scaffold to understand how a body like the current visitor could be kept, grown, and recognized by its marks. We do not need it to be the whole story of planet formation. We only need it to be part of the story that closes the timing gap without special pleading. Set a gentle question beside you as the light fades around the frame. If worlds are sometimes adopted rather than solely self-made, how would that change the way we read our own neighborhood, where giants sit in places that still surprise us? The answer is not due tonight. It is enough to let the thought rest while we go look for the fingerprints that a good adoption would leave, like a pocket, warm and sure. Across a young star's cradle, a wanderer cuts through invisible air. It is fast, nearly free. Ahead lies a wide, quiet medium. If it breathes enough, if it yields enough, that medium can keep it. Think first in pictures, then in numbers. A small dark body arrives on a steep, open curve. Around the star spreads a thin ocean of gas and dust, not thick like Earth's air, yet broad enough to matter across millions of miles. The traveler is wrapped in a bright envelope of molecules and grains. That envelope is not decoration. It is a parachute that opens itself. The physics is plain, almost domestic. Move through gas, and you feel a headwind. That headwind robs motion and turns it into heat and turbulence. If gravity is nearby, some of that loss can be traded for a tighter curve. Do it once, and you only bend. Do it again and again, and you drop into a loop. Once in a loop, you meet the gas more often. Each meeting trims more speed. The loop tightens until it becomes residence. Two hard facts give this scene its floor. Young stars are commonly wrapped by gas-rich disks that thin over a few million years. Bodies that plow through gas experience aerodynamic drag, which extracts kinetic energy. If enough energy is lost while gravity holds the path close, an unbound orbit can become a bound one. Everything else here is detail on those truths. Now, a compact cluster of rounded numbers to keep the desk honest, and then we return to calm images. A typical interstellar approach, speed far from the star, can be on the order of a few tens of kilometers per second. A kilometer-scale nucleus with a coma thousands of kilometers wide presents an area that far exceeds its solid face. Gas densities in inner regions of a young disk are many orders of magnitude thinner than air, yet the crossing distance is so large that even tiny drag, integrated, can remove a useful sliver of speed. A single deep plunge might shave a fraction of a percent. A handful of grazes over months to years can add up to the several percent needed for a loose loop to close. Gravitational focusing is the quiet ally in this process. Gravity, from the star and the disk, bends the incoming path, which increases the time spent inside the gas and the chance that drag will matter. If the traveler already carries a veil, focusing works on a bigger target. You can think of it as the difference between catching a pebble and catching a dandelion puff. The pebble slips by. The puff lingers on your palm. There is a vivid image that holds the whole method in one breath. Picture a coal ember skimming along a bank of fog. It hisses very softly as it passes, dulls by a sliver, and its curve deepens. The ember returns for another skim, gives up another sliver, and the fog accepts the ember into a wide, slow dance. Nothing dramatic happens, only contact, repetition, and time. The envelope matters twice. First, it multiplies drag by increasing area relative to mass. Second, it feeds itself. Carbon dioxide can wake far from the star, keeping the coma alive early. Water joins later, thickening the flow. Dust lifted into that coma adds still more area. The brighter the breath, the stronger the break. That is why this visitor's chemistry interests people who think about capture. The same composition that makes it easy to read also makes it easier to slow. A grounded speculation follows from that chemistry without asking for anything exotic. In a disk that still holds gas, a body with a CO2 forward coma would begin losing speed before the inner regions are reached. The loss would not be large per mile. It would be patient. If the path threads the disk more than once, or if the first plunge is deep enough to raise more vents, capture becomes plausible. Not certain, not frequent everywhere, but plausible in the environments that matter for building giants. Drag alone is not the only brake available. Gas can also torque a path, especially if the body's envelope is asymmetric. Vents that point into the flow push differently than vents that trail. Rotation brings those vents in and out of the wind like paddles. Over many spins, the net force is not zero. A careful observer can read that pattern in the way gas production pulses with period. The same rhythm that lets us estimate a spin rate informs us about how the brake is applied. Keep a small, dry smile on the page for the engineer who looks at this and murmurs that it is simply aerobraking writ large. It is, except the craft is not designed and the medium is not a neat shell. It is patchy, layered, and full of slow weather. That is why capture is rarely a single pass event. It usually asks for a grazing membership, a set of meetings that each give up a little, until the traveler cannot leave. Dust plays a subtler role that is easy to miss. If grains are fragile and porous, they present more cross-section for the same mass, increasing drag. If grains are compact, they scatter light differently and change how the envelope cools, which changes how vents behave. Polarization measurements, which at first glance sound like pure optics, therefore reach into dynamics. When we say the dust remembers a different nursery, we're also saying the brake will feel different when that dust is stirred. Now, step back and draw the flow cleanly from encounter to residence. An interstellar object arrives with excess speed and an active veil. Gravitational focusing bends it toward the plane. Drag drains a small amount of energy. If the path closes enough to loop, subsequent passes through thicker regions increase the loss. Once the orbit is bound within the disk, pebbles and gas stream inward. The small body that arrived as a stranger begins to grow from local material. The veil that once slowed it now feeds it by sweeping grains into its hill of influence. There are natural limits. If the body is too large and the envelope too thin, inertia wins and the passes are too quick to matter. If the body is too small, it can be shredded or pushed aside without gaining much mass. Between those extremes lies a practical size where survival, activity, and drag cooperate. That is the quiet Goldilocks zone for adoption. A brief technical breath, clustered again. The timescale to close a loose loop depends on relative speed, gas density, path length inside the disk, and the ratio of cross-section to mass. Increase the envelope by a factor of a few, and the required number of passes drops by a similar factor. A path that would have slipped through in one brush can become a temporary member that returns for another. Give that membership a few returns, and the transition to residence is no longer optimistic. It is expected. Once residence begins, The role of gas changes. It is no longer only a brake. It becomes a supplier. Gas drag shepherds pebbles into the growing body's gravity well. The same flow that trimmed speed now delivers calories. In models, this is where growth can jump from a slow diet to a feast because the core is heavy enough to gather gas directly. The clock that once hounded the process is suddenly friendly. There is still time left in the disk. What would seal this picture are the fingerprints of adoption left on finished worlds. If captured seeds are real contributors, some giants should carry atmospheric blends that do not match their stars. Elemental ratios might tilt quietly. Isotopic ratios could whisper of a nursery with a different metallicity. Migration can blur lines, but statistics can unblur them. That is why the method lives or dies not on a single traveler, but on a population and on careful comparisons between planets and their suns. Hold one vivid image as the instruments keep working. A moth meets a slow fan, not strong enough to throw it away, not weak enough to ignore. Each touch steals a little speed. After a while, the moth is in the room, and the air is all it needs to stay. A gentle question to carry forward. How often does a young disc meet a visitor with the right size, the right veil, and the right angle? And how many quiet adoptions would it take to explain the giants we see? Imagine the small surrender that changes a life. A few percent of speed given to a quiet medium, and a free path becomes a long stay. Rest with that idea while the instruments keep watch, like a pocket, warm and sure. A captured body drifts in the disk, like a coal settling into a slow forge. The air is thin, the heat is patient, but the setting is perfect. If the core is ready, the flame becomes a flood. Picture the neighborhood after adoption. Gas flows along pressure lanes. Pebbles drift inward like quiet conveyor belts. And the captured body sits where the current converges. Around it, gravity claims a sphere of influence that is small on the map, but enormous compared to the nucleus. Within that sphere, the rules change from wandering to feeding. Keep the compact numbers in one breath, then let them go. Disks rich in gas fade in roughly 3 million years. A heavy heart near 10 Earth masses invites fast inflow. Once enveloped cooling begins in earnest, the timescale for runaway gas capture can drop to around 1 million years or less under favorable conditions. What was once a race becomes a glide. 2 hard facts to ground the scene. First, a core that crosses a threshold near 10 Earth masses can bind and cool an atmosphere efficiently, which accelerates gas accretion. Second, inward drifting pebbles do not stop at the planet's orbit. Drag guides them toward the growing gravity well, enhancing the supply. These are not embellishments. They are the quiet mechanics of how disks behave. A vivid image to hold. Think of a lamp wick touching oil. At first, the flame wavers. Then the reservoir connects, and the wick brightens without hurry. The core is the wick. The disk is the oil. The brightness is the brief, decisive phase when mass pours in. What changes immediately after capture is geometry. The body's hill sphere, once a mere sketch, becomes a working intake. Gas doesn't crash straight in. It spirals, cools, and settles. Pebbles entering that sphere are slowed by gas and by collisions, then join the envelope or rain onto the core. Each grain adds density and liberates energy as it falls. That energy must be radiated for collapse to proceed. The better the envelope sheds heat, the faster the body can accept more gas. Now, a compact cluster of processes gathered and set down. Cooling controls collapse. Opacity controls cooling. Dust in the envelope sets the opacity, and dust supply is affected by the very pebbles the disk delivers. Meanwhile, the body carves a shallow gap in the gas that both feeds it and limits it, balancing the inflow with the disk's ability to refill the lane. Migration tugs at the orbit, shifting the intake through regions of new chemistry. The whole picture is slow motion, yet decisive on the disk's short clock. Here is the grounded speculation that matters for our seed path. If the core didn't have to be built locally and arrived already near the critical mass, then envelope cooling begins sooner, runaway begins sooner, and the giant finishes while gas is still abundant. The shortcut is not a loophole. It is an allowed rearrangement of steps that obeys the same physics as the classic path. Think for a moment about chemistry riding on dynamics. A foreign core may start with a slightly different blend of refractory material. As pebbles add local dust, and as gas condenses, the mix dilutes toward the disk average, yet traces can persist. Heavy elements can be overrepresented compared to a planet built entirely from local light gases. Later, when we read a giant's atmosphere, we might see that quiet enrichment as a fingerprint of an unusual beginning. Two more steady facts, then back to pictures. Accretion luminosity can be high during the rapid phase, enough to puff the envelope until cooling catches up. And once the planet opens a deeper gap, the gas supply throttles and growth slows, which is why the runaway phase is brief compared to the calmer years that follow. The signature is a short, vivid climb and a long, quiet plateau. Return to the forge image and let it deepen. The disk is not a uniform fire. It is a set of warm lanes and cooler shadows. The captured body lives where those lanes bend. Streams of pebbles spiral like slow sparks. Gas moves as wind you cannot see, but you can read it in how small things drift. The core drinks from both streams. It glows from the inside, then breathes that heat away to keep drinking. The practical Goldilocks window appears again. Too small a core, and the flame never stabilizes. Too large a core, arriving too late, and the oil is gone. The sweet spot is a few kilometers across at the beginning if we are speaking about the seed itself, and tens of earth masses if we are speaking about the threshold heart. Between those scales lies the ladder that the seed climbs with help from the disk. There is a gentle but useful caution. The same head start that solves the clock also entangles the new planet with migration. As the growing body disturbs the disk, torques push it inward or outward depending on local gradients. In some systems, a seed-turned giant may not end where it began. That motion complicates the search for fingerprints, but it also increases the chance that giants end up close enough for our instruments to study. Hold another image to rest the mind while the numbers settle. Imagine a light rain over a broad basin. A small cup sits at a low point. At first, the cup catches droplets. Then a channel forms, and water begins to arrive along a path. The cup fills quickly, not because the rain is heavy, but because the geometry favors the intake. Capture is the cup. The channel is pebble drift. The fill is runaway. What would we look for in the sky to confirm this path? We would expect some giants to show metal enrichment above their stars' averages, especially if the seeds spent time gathering solids before gas dominated. We would expect correlations between heavy element content and where in the disk the object seems to have grown. We might even expect a few cases with isotopic hints that do not sit neatly on local lines. None of these alone is a verdict. Together, they make a profile that statistics can weigh. There is a small, dry joke the sleepy physicist makes when the whiteboard fills up. The miracle here is not that giants form. It is that they stop. The runaway phase wants to keep going until the lane is empty. Gaps, torques, and the disk's own decline are what keep worlds at sizes we can live with. Set the open question down softly at the edge of the desk. If a fraction of giants began with adopted cores that leaped the slowest step, how large a fraction would be enough to explain what surveys already see? And where should we point our instruments next to find their quiet marks? The forge dims for now, but the cup is still in the rain. Let that picture linger as a calm ending. A ready heart, a patient medium, and a brief window when the two fit like a pocket, warm and sure. A world can hide its birth, but it cannot hide its chemistry. Think of an atmosphere as a quiet confession. Light passes through, molecules hum, and the spectrum writes a line that tells you where the pieces came from and how they met. Begin with what a fingerprint means in practice. When starlight filters through a planet's air during a transit, certain wavelengths are dimmed by water, carbon monoxide, carbon dioxide, methane, ammonia, and a family of lesser voices. Reflected light does the same from another angle. Emission from the planet's own heat adds a third perspective. Stitch those views together, and you get ratios of elements, ratios of isotopes, and hints about cloud material falling out of the sky. If a core was adopted from elsewhere, some of those ratios should refuse to match the star it circles. Two hard facts give this idea weight. First hard fact: a planet's bulk composition is not obliged to mirror its star. Many giants show heavy element enrichment compared to their hosts, and that enrichment varies with planetary mass. Second hard fact: isotopic ratios, like deuterium to hydrogen and nitrogen, 15 to nitrogen 14, carry a memory of temperature and origin. These ratios have been used in our own system to track where ice is formed and how they moved. The same logic applies to exoplanets when the data are clean. Now, the compact technical breath, so the numbers live in one place, and then let us return to images. Strong near-infrared bands sit near 1.4, 2.3, and 4.3 microns for water, methane, and carbon dioxide. Carbon monoxide shows cleanly near 2.3 and 4.6 microns. Modern spectrographs span roughly 1 to 5 microns at resolving powers from about 1,000 to 100,000. That range lets us read broad features for abundances and sometimes narrower lines for isotopes. Clouds mute amplitudes, so we also look for alkali metals near 0.6 to 0.9 microns and thermal slopes in the mid-infrared to infra hazes. What does a captured core predict? Start with elemental ratios. A foreign nucleus can tilt the pantry before the disk's gas finishes the meal. If the seed brought more refractory material, the finished giant's atmosphere may be metal-rich compared to the star. If the seed formed in a carbon-friendly nursery, the carbon-to-oxygen ratio can skew upward, especially if water ice delivery lagged behind hydrocarbons. These skews are not cartoons. They are small, stubborn biases that persist after the planet migrates. Isotopes add finer grain. Deuterium prefers colder formation. Nitrogen's heavier isotope tracks chemical pathways that favor low temperatures and long storage in ices. Carbon 13 to carbon 12. Oxygen 18 to oxygen 16. Sulfur 34 to sulfur 32, each with its own sensitivity. A seed that spent ages in a cold belt under a distant star could carry an ice inventory with quietly different isotopic mixes. When gas accretes, those mixes are diluted but not erased. The result is a planet that whispers of a nursery it never orbited. A vivid image to hold the method. Imagine a violin made from spruce that grew on one slope rather than another. The instrument looks the same to the eye, but under a bow, it reveals a timbre that woodworkers can hear. A giant planet is the same kind of instrument. The star provides the strings. The core provides the wood. The song tells you both. Consider noble gases. Argon, krypton, and xenon do not react easily. They are traveler's coins that pass unchanged from pocket to pocket. In cold regimes, they can be trapped in ices and carried inward. If a seed formed where noble gases froze efficiently, and if delivery happened before high temperatures drove them off, a finished planet could show noble gas enrichments that outpace simple models tied to the star. Those enrichments are difficult to measure, but they are powerful when they appear because they point to cold starts. Clouds and condensates become evidence when placed in context. Silicate and iron clouds form high in some hot atmospheres. Sulfide and chloride clouds form deeper and cooler. If a planet carries an unusual balance of sodium, potassium, or silicon in its upper layers, it can hint at deeper heavy element reservoirs that began with a seed. The trick is to separate what the atmosphere is doing now from what the interior inherited. That is where comparisons between planets around the same star help. Shared light, different outcomes. There is a grounded speculation that follows naturally. A small set of hot giants with supersolar metallicities and carbon to oxygen ratios at the upper edge of current measurements could be descendants of captured cores. The adoption would not be obvious. It would be inferred from a mismatch between the planet's blend and the stars. from noble gas or nitrogen ratios that lean cold, and from heavy element budgets that look too generous for purely local assembly. No single sign would be decisive. Together, they would form a profile that is difficult to explain away. Keep the observational path realistic. Transit spectroscopy provides broad chemical strokes for close-in planets. High-resolution cross-correlation on large telescopes can isolate carbon monoxide and water even when the signal is faint. Direct imaging can do the same for wide, young giants whose heat makes them bright. Combine these with stellar abundances from high-quality spectra, and you have the ingredients for a fair comparison. The test is not mystical. It is a side-by-side ledger. What about the seed itself, still passing under our sun? The chemistry we read in its coma is not a planet's atmosphere, but it does tell us what kind of pantry a seed can carry. Carbon dioxide, forward activity, water joining later, and dust that hints at different grain structures all point to a style of cargo that, if captured, would color the early steps of a world. That is why the visitor matters to this chapter. It turns the fingerprints from abstract possibilities into something you can actually imagine moving through a disk. One more compact cluster to keep the desk straight. Abundance retrievals return logarithmic metallicities relative to hydrogen and ratios like carbon to oxygen, with uncertainties that widen when clouds are thick. Isotopic detection needs high signal and often high resolution. Noble gases are rare winds. Interior heavy element masses are inferred from gravity and radius, then compared with atmospheric metals to look for gradients. None of these measurements stands alone. The strength comes from convergence, a second vivid image to rest the mind. Picture a window pane in cold air. You breathe on it, and it fogs. Your fingerprint appears where you touched the glass hours ago. The planet's spectrum is that fog, and the seed's composition is the print beneath. You cannot see it without help, but when the conditions are right, it stands out. It is fair to ask whether stellar scatter can mimic everything a seed might do. Stars themselves vary in metallicity. Disks fractionate material. Migration drags planets through different kitchens. The honest answer is that nature does blur the lines, which is why we ask for statistical clarity instead of singular claims. If a subset of planets around stars with similar compositions shows the same defiant tilts in metals, isotopes, or noble gases, then the adoption story gains weight. If the tilts track only with local disk gradients, the seed story retreats to a quieter role. There is also the possibility of layered histories. A planet might start on a local core, then swallow a foreign body later, and bury that composition beneath new gas. Or a foreign core might arrive and then be overgrown so completely that only a faint isotopic seam remains. In that sense, the fingerprints we seek are not clean loops on a card. They are smudges along a margin that require patience to read. Set down the gentle question that should follow you into the next scene. When we compare a planet's song to its star's rhythm, how much difference counts as heritage rather than weather? And how will we decide when the notes are close but not the same? A quiet closing for now. Spectra are on their way for many worlds. Ratios will settle, uncertainties will narrow, and patterns will either emerge or fade. If adoption leaves a mark, it'll be small and stubborn. That is the kind worth listening for, like a pocket, warm and sure. Night holds steady, and a thought sharpens like a compass point. If a young system can adopt a traveler and grow it fast, then the familiar diagrams are not wrong, only incomplete. The instructions need an extra page. Start from what is firm, then allow the rest to follow. Observations tell us that gas-rich disks thin out in only a few million years. Surveys of exoplanets show that giant worlds are not rare, and many carry heavy element budgets that exceed simple copies of their stars. We have now seen several interstellar visitors, at least one with a living envelope rich in carbon dioxide that wakes early and stays readable. Those are the stones we can step on without slipping. Numbers belong in one breath. Then we return to quiet water. Disk lifetimes, roughly 3 million years. A threshold core near 10 Earth masses. The runaway phase, about 1 million years when conditions align. Visitor nuclei, often on the order of 1 to 5 kilometers when active. Enough to guide the mind, not to crowd it. What changes under this proposal is the order of operations, not the physics. The classical path builds the heart locally then. If the clock has not run out, the gas pours in. The expanded path allows some hearts to arrive ready, or nearly so, which moves the slowest step off the critical path. Capture through gas drag is not a trick. It is a patient conversion of motion into residence. Once residence begins, the disk that slowed the body becomes the disk that feeds it. Two hard facts anchor that shift. First, aerodynamic drag in a gaseous medium always removes kinetic energy. Second, bodies with wide envelopes present larger effective areas, which raises drag for the same mass. The current visitor's CO2 forward coma makes that second point practical rather than abstract. Early activity increases area long before the warmest regions are reached. A vivid image to hold as the ideas reassemble. Picture a carpenter's square laying against a new line on old wood. The board has not changed, only the angle of the cut. The piece that falls away makes room for a joint that fits. The rulebook is the wood. The seed path is the new line. Skeptics are right to demand more than a clean image. They ask whether a disk meets enough candidates while gas remains, whether capture is efficient at real speeds, and whether adopted cores survive the long crossing intact. The cautious answers are that encounter rates rise with better surveys, that efficiency improves in repeated grazes where envelopes are bright, and that survival favors moderate sizes that neither shatter nor ignore the headwind. None of those answers rests on optimism. They rest on integrals of small effects over large distances and times. Grounded speculation turns those answers into testable predictions. If adoption contributes even a modest share, then some giants should show atmospheric ratios that refuse to mirror their stars, especially in heavy elements and in isotopes that record cold origins. There should be a preferred size among interstellar bodies, that balances survival and drag. Objects that wake with carbon dioxide far from a star should be overrepresented among plausible seeds, because early activity multiplies the break that capture needs. A second image, more tactile, to settle the concept. Think of a notebook where new pages are taped into the middle, not at the end. The story does not change its beginning or its conclusion, but the middle gains a bridge that was missing. The seed idea is not a replacement for the local build. It is the taped-in chapter that connects the clock to the outcome in more than one way. What counts as evidence that the tape belongs there? Start small. Look for clusters of giants whose metallicities and carbon to oxygen ratios sit above their stellar baselines in the same subtle way. Look for worlds that carry noble gas enrichments that are awkward to explain with only local condensation. Compare planets within the same system. Shared light is a powerful control. If one world declines to match its siblings under the same star, ask why. Keep the compact mechanics in sight, because they are the gears that turn the story. Drag grows with area, so active envelopes matter twice, for slowing and for sweeping pebbles inward. Gravitational focusing stretches interaction time, which gives drag a better lever. Once a loose loop closes, cooling and opacity decide how quickly gas can settle. A bright, dusty envelope raises opacity until grains sink or are burned off. Then cooling accelerates and the flow deepens. Nothing here is mystical. Each piece has been studied for other reasons. The novelty is their order. There's a quiet discipline hidden in the way this new page is read. The words seeded and adopted can bend into romance. If we let them, we will not. The path succeeds or fails on populations, not on a single charismatic visitor, and not on clever analogies. The test lives in tallies. How many interstellar objects we find and what their chemistries look like. How many giants show mismatches with their stars. How those mismatches correlate with mass and orbit. The proposal does change our sense of place, but even that change is modest and empirical. If some worlds begin as strangers, then planetary systems are not sealed workshops. They're open studios that trade materials across long reaches of time. The Milky Way becomes not only a field of isolated families, but a neighborhood where doors are sometimes left ajar. The sentiment is gentle. The claim is practical. Exchange is allowed by the physics and suggested by the evidence. It also clarifies why giants so often feel like overachievers. Local growth alone can fight the clock, but it needs the perfect corridor of pressure bumps and pebble flows at the perfect hour. An adopted core needs something simpler, a meeting while gas still hangs in the air. The first path remains valid where the corridor exists. The second path takes over where it does not. Before we close, gather the compact expectations that guide the next measurements. Disks disperse quickly, so any solution must shorten the early steps. Interstellar visitors are diverse, so a subset should show chemistries that keep envelopes wide at large distances. Capture should favor moderate sizes that offer cross-section without crushing inertia. Planets that result should carry quiet overabundances and isotopic tilts that outlast migration. Each expectation points to a specific observation we either have or will soon have. Now, soften the view, because this is where the rulebook becomes a comfort rather than a contest. The new page does not scold the old ones. It completes them. It says that worlds can begin in more than one way, and that the cosmos is generous with roots when time is short. The carpenter's square lays along both cuts, and both joints can hold. A gentle question to keep as we step aside for a moment. When our census is richer and our spectra cleaner, will this new page read like a margin note, important in some places and quiet in others? Or will it read like a central paragraph that many systems depend on? Closing this movement, let the room dim a little more. Imagine a table where instruments sleep between nights, and beside them, a notebook with a fresh line penciled in. The line doesn't erase the older writing. It threads through it, joining parts that needed a bridge. Somewhere, a small body moves under a calm star, and a set of rules waits to be tested against its light. The next act is already in motion, not loud, not rushed, only steady. We will follow where the evidence gathers and let the new page find its place, like a pocket, warm and sure. The notebook from before lies open, a fresh line drawn through familiar rules. Instruments wake one by one, lenses cooling to focus. Out beyond Mars, the traveler exhales. The veil brightens, not with water alone, but with a cooler breath that stirs earlier. We turn the page from method to machinery and ask what powers this steady glow. Picture a compact body with hairline seams in a sunlit chill. Through those seams, a faint gas slips free and lifts powder into a pale halo. This is not dramatic. It is dependable. Carbon dioxide wakes before water, and that head start matters when every day of drag is part of the calculus. Two hard facts to lay down first. Carbon dioxide sublimates at lower temperatures than water ice, so it can drive activity at larger solar distances where water remains quiet. Its strongest emission sits near 4.3 microns in the infrared, a clean marker that lets spectrographs confirm its presence even during a single, fast passage. Those two notes turn a hunch into a plan. Keep the compact parameters in one breath, then let them go. Water ice tends to become efficient close to the sun, within a few astronomical units for small bodies. Carbon dioxide can wake earlier, adding gentle thrust and lifting fine grains when sunlight is still weak. Typical coma scales expand to many thousands of kilometers, far larger than a kilometer scale nucleus, which multiplies the area that meets any medium it enters. If the medium is a gas disk around a young star, that area becomes a break. A vivid image to hold the mechanics in your hand. Think of a cool bellows feeding a slow ember. The ember does not flare, it steadies, and that steady breath keeps a light alive across a long walk. Carbon dioxide is the bellows. Water is the later flame. Together, they make endurance. This is where the idea stops being decoration and becomes function. A seed that wakes on carbon dioxide alone can build an envelope in conditions that look empty to water. That envelope increases cross-section, which increases drag, which raises the odds that a young disk can keep what it meets. Later, nearer a star, water joins and the envelope thickens. The same chemistry that helps us see the traveler helps a disk slow it. One purpose, two uses. Dust turns the bellows into a sail. The first carbon dioxide jets entrain finds that are light, porous, and abundant. Such grains scatter light with strong polarization signatures and, more importantly for dynamics, present a large area for their mass. If those grains are common, the envelope becomes both a better reflector and a better break. Later, as water wakes, larger particles are lifted. The veil grows denser, the sail stiffens, and drag grows again. Second hard fact for the table. Even in our own system, distant comets often show carbon dioxide-driven activity well before water takes over. The physics is the same out there as it is here. Energy from sunlight releases gas. Gas lifts dust, and the two together shape what follows. We are not inventing a new engine. We are recognizing it in a new traveler. Now, a compact cluster about storage and release, placed once and then left. Carbon dioxide can be present as its own ice, trapped in amorphous water ice, or bottled in clatrates. Each storage mode has a different release temperature and a different reaction to repeated heating. If the traveler's surface carries a patchwork of these reservoirs, the early activity will pulse as the rotation brings vents into light, then smooth as fresh surfaces are exposed near the warmest part of the path. That evolution is a diagnostic. It tells you how deep the pantry runs. A grounded speculation follows that stays within what the instruments can test. A body that formed in a colder belt under a different star may keep more near-surface carbon dioxide than many comets we catalog here. That would explain why it wakes earlier and why the veil is durable at modest heat. It would also prepare the body to act as a seed in a gas disk by presenting a wide, persistent cross-section before water awakens. No extra physics, only a different stocking of the shelves. Return to images for a moment, because they help the hands remember what the mind just weighed. Imagine a small black kiln in a winter field. It leaks a pale breath that never quite stops. As the day warms, a second breath joins, heavier and richer. The kiln does not explode into flame. It continues to exhale, and what matters is the constancy. Capture is not a sprint. It is an accumulation of tiny deficits in speed. Constancy wins. Numbers belong in one place. The traveler's nucleus sits in the modest range, roughly fractions of a kilometer to a few kilometers, if it is like many active visitors. The coma swells to thousands of kilometers, a soft disk in space. Carbon dioxide's band near 4.3 microns, and water's strong features near 2.7 microns and beyond 5 microns gave observers a paired meter to log production. When those bands rise and fall with a rotating rhythm, the spin period emerges. which maps where the vents live. That map speaks to crust strength and layering, the quiet engineering that decides how an engine breathes. Here is a subtle advantage of a carbon dioxide first design. Early activity tends to seal as well as open. When gas refreezes at night or on the dark side, thin crusts grow along cracks and pits. These can redirect later flow, turning vents into nozzles that amplify thrust without tearing the body apart. That geometry is helpful for persistence and helpful for capture, since an organized envelope stays broad without shredding itself into boulders. A second subtle advantage lies in thermal bookkeeping. Carbon dioxide cooling effects at the vent can limit local erosion, which lengthens the life of the engine. Water, once active, carries more mass and can erode faster. A seed that begins with carbon dioxide and passes the baton to water near a star has enjoyed both endurance and strength at the right times. The handoff is the strategy. It widens the window where the body can present drag without premature failure. If this is the machinery, what marks would we expect to see across a single pass? First, a measurable carbon dioxide flux at distances where many small comets sleep. Second, a transition toward water-dominated flow as heat climbs, often with a richer dust load and a thicker halo. Third, a spin-linked pulsing in both gases, telling us vents are localized and crusts have strength. Those three are not guesses. Their signatures our instruments can seek deliberately. A vivid image to fix those signatures in place. Think of a watch spring catching light in a slow turn. One bright, one dim, again and again. The brightness is not a mood. It is the angle of a vent that opens and closes to the sun. Watch long enough, and the period appears. Now, you know how the engine ticks. Two questions often arrive here, and they are healthy. Is carbon dioxide truly dominant, or are we fooled by geometry and temperature? Are we sure dust behavior reflects grain structure rather than just viewing angle? The safe answer is to watch the curve with patience from multiple angles and to compare instruments. If the same lines rise first at large distances in repeated observations, the role of carbon dioxide is secured. If polarization patterns remain unusual as the viewing angle changes, the dust memory is real. The destination is practical. If a seed is a working concept, it must be a working engine. Carbon dioxide gives it a starter motor that turns in the cold. Water gives it torque near the fire. And dust gives it the flywheel that keeps the system broad and effective. That trio ties chemistry to dynamics in a way that a young disk can use. Let a quiet question close the page and open the next. How deep is the carbon dioxide pantry in this traveler? And does its rhythm suggest a surface patched by many winters, or a body that kept its oldest seams intact? For now, let the kiln breathe in the dark field and the bellows keep time. We will follow the breath as the light grows and see if the engine holds its tune like a pocket, warm and sure. A pale halo folds thicker and bluer, and the spectrum sharpens like handwriting. In the glow are two voices that matter for beginnings. One is water, waking late and strong. The other is a faint cyan trace, a clue to deeper chemistry. Set the scene with the simplest picture. Sunlight warms a crust, seams open, and vapor escapes. At first, carbon dioxide lifts fines. Closer in, water joins, heavier and louder, dragging larger grains. In that louder breath, observers look for narrow signatures from reactive fragments that betray complex parents. Among the most useful is the violet glow we call CN, a stand-in for nitrile chemistry higher up the chain. Two hard facts, stated cleanly. Water vapor in a cometary coma is a direct sign of near-surface ice sublimating. Its infrared bands let us track production as sunlight rises. And CN emission is a standard tracer in comet science, formed by photodissociation of nitriles such as HCN, which lets small telescopes map organic activity even when other bands are faint. Those facts turn poetic talk about cargo into measurable quantities. Now a compact breadth of parameters. Then we return to quiet. Water's strongest bands for these studies cluster near 2.7 microns and beyond 5 microns. Can glows around 388 nanometers. Production rates in active comae often climb by factors of a few as distance to the sun shrinks. Dust cross-sections expand to thousands of kilometers, letting gas and light work together as a readable plume. Hold a vivid image of what that plume might carry. Imagine a sealed ampule tucked inside a traveler's dark suitcase. What leaks first is the lightest solvent. What follows are the bottles with labels worn thin. Alcohols, nitriles, simple acids, sulfur notes. The suitcase is not a metaphor for life. It is a pantry of precursors, the sort chemistry uses to build larger scaffolds when heat and minerals make a proper bench. Ground the imagination with established cases. In our own system, missions and telescopes have found methanol, formaldehyde, HCN, and more in comet comae. The Rosetta mission at 67P detected glycine, the simplest amino acid, along with other small organics. None of this proves biology. It proves that icy bodies can stock and ferry raw ingredients far from where they formed, and that those ingredients can endure cycles of heating and cooling without erasing themselves completely. Why does this matter? For a seed, because a captured body would not only provide a ready-made core, it could also seed the nearby disk or the envelope of the growing planet with water and organic feedstock at the very moment the system is best able to use them. Warmed grains stick more easily. Surfaces catalyze reactions. Ultraviolet light and shocks in the disk drive simple molecules into slightly more elaborate shapes. The pantry arrives on the day the kitchen opens. A second hard fact, easy to overlook because it is small. Dust shields chemistry. Porous grains, lifted by early gas, cast local shade and provide surfaces where molecules can stick, recombine, and hide from harsh light. A veil rich in fines acts like a traveling canopy for fragile species. Protection is not perfect, but it slows destruction enough for delivery to matter. In a gas disk, that veil does double duty, both as a chemical shelter and has extra area for drag. You can hear a cautious voice ask whether organics survive capture heating. The safe answer is that some always do. Many nitriles and alcohols are volatile, but not instantly lost, especially when trapped in ices or clathrates or bound to grain surfaces. Night-side refreezing and self-shadowed pits preserve pockets even as dayside vents roar. In other words, traffic is largely at the surface, while deeper stores remain in reserve until the geometry changes. There is a practical rhythm to how these materials would be handed off. Early in the approach, carbon dioxide lifts fines, peppered with simple organics. Closer in, water flow thickens and can ferry larger, mineral-rich grains. Those grains matter because minerals catalyze. Iron sulfides, clays, and amorphous silicates provide sites where carbon chemistry can climb a rung, especially if intermittent heating and cooling pass the baton back and forth. A seed that leaks both solvent and solute becomes more than a courier. It becomes a mobile lab, small but serviceable. Keep the numbers clustered again, then release them. Typical grains in active coma range from submicron powder to millimeter pebbles. Porosities can be high, creating vast internal surface area. Photons in the ultraviolet split HCN on timescales of hours to days in sunlight, feeding CN while leaving much of the bulk inventory untouched below a few millimeters. These are practical scales for survival and for delivery. A grounded speculation follows directly. If this traveler were captured in a young disk, its earliest leaks would enrich the local gas with water and nitriles while the dust veil broadened drag. As the path tightened and water vents deepened, heavier grains would rain inward. Some fraction would fall onto the growing core and mix into its envelope. Some would be swept by disk winds and recycled through pressure bumps, feeding chemistry far from the nucleus itself. The net is not a delicate miracle. It is a set of ordinary transfers in an environment tuned to accept them. There is also a gentle inversion to consider. We usually think of comets delivering organics to rocky surfaces late, after planets cool. The seed idea adds an earlier route. Delivery happens while a world is still becoming a world. When its envelope is young and its temperature field is complex, the timing changes what chemistry can do. High temperatures destroy, but gradient fronts and cool eddies also sort and preserve. Adoption could bake certain molecules into deeper layers where they linger as tracers long after the surface forgets. A second vivid image to keep the idea tangible. Picture a traveling archive, thin books bound in frost. Some pages smear when you touch them, others hold firm. The important thing is not that every word survives. It is that enough do to keep the story legible after the move. Skeptics will ask whether the CN we read now proves anything about futures elsewhere. The honest, careful line is that CN is a proxy, not a pedigree. It tells you that nitriles are in play, that ultraviolet light is tearing them into tracers we can see, and that the parent stock is not empty. From that baseline, we look for corroboration in other bands and in dust behavior. If the signals persist across geometry and time, the case strengthens from mood to measurement. There is a small, dry joke that fits here. Seeds that smell faintly of almonds do not promise a tree. They promise a nursery that stocked almonds. The difference matters. It keeps our curiosity inside the lab, where it belongs. Let the practical tests settle on the table. Watch whether water and CN flux rise together or in offset phases as the body warms. Compare production rates to dust polarization to infer how grains change as vents deepen. Track whether the heaviest rains of grains align with the highest water output. Each of those relationships sits close to the physics of capture and the chemistry of delivery. Each has a consequence for whether a seed is function as well as metaphor. The open question to carry forward is precise and light. How much of this cargo would reach a young world's envelope or surface intact? And how much would be reprocessed into a different inventory along the way? The answer will not arrive in one pass. It will arrive as a pattern across many travelers and many planets. For now, let the halo breathe and the archive ride in its shade. The suitcase does not explain life. It explains a tendency where water and organics move together under patient light. Chemistry finds ways to practice, and practice matters, like a pocket, warm and sure. In the blue hush before dawn, the halo thickens and glitters. A few spectral lines flare where metal should speak, and one voice is louder than expected. The solids begin to tell their story. Begin with what refractories mean for a traveler like this. Volatile ices give it breath, but metals and rocky grains give it backbone. They set thermal inertia, crust strength, and how vents organize. They also carry a memory of the furnace where the first solids condensed. Nickel and iron are the classic pair in that memory. In meteorites and many comets, they travel together, close in both origin and abundance. When that partnership loosens, people notice. Two hard facts. First, set down cleanly. Nickel and iron are established constituents of cometary comets and dust, detected in emission lines and in returned samples from our own system. Polarimetry of cometary dust is a proven diagnostic of grain structure and porosity with a characteristic negative polarization at small phase angles that shifts with composition and texture. Those two anchors let us read chemistry and structure without touching the body. Now, a compact cluster of technique. Then we return to calm pictures. High-resolution spectrographs isolate weak metal lines riding on the brighter gas continuum. The relative strengths of nickel and iron features provide a quick comparison against expectations from solar or meteoritic ratios. Polarimetric measurements track how scattered light twists with viewing angle. Porous aggregates, organics, and compact silicates each leave a different curve. Place those tools together and you can sketch both what the dust is and how it was made. The puzzle arrives in whispers, not shouts. Observers report nickel features that are easier to see than iron lines of similar strength under comparable conditions. That does not mean iron is absent. It suggests an imbalance in the part of the coma that glows, or a preference for nickel to appear in the gas phase, while iron stays locked in grains or compounds that do not give up atoms as easily. The result is a spectrum that feels tilted, a ledger where one column has more entries than the other, a vivid image to hold the idea. Picture two bells, cast from the same workshop. Struck together, they usually ring in harmony. Tonight, one carries clear, the other damped by a cloth you cannot see. The hall is the coma. The cloth is whatever keeps iron quiet. What could the cloth be? Grounded speculation favors chemistry and grain structure more than magic. Iron is happy in sulfides and oxides that can cling stubbornly to grains. Nickel, though often partnered with iron, can be liberated from different surface sites or sputtered more efficiently by ultraviolet light. If the grains are porous and fragile, with large surface area, a small difference in binding can become a noticeable difference in emission. The tilt in the spectrum would then be a surface phenomenon, not a statement about the deep interior. Dust behavior points to the same kind of surface story. Early polarimetry hints at a strong negative branch and a slope that leans toward porous aggregates, the kind that form in gentle environments with low compaction. Such fluffy grains scatter light in a way that both increases polarization signals and changes how heat moves through the coma. They cool efficiently. They carry organics on broad surfaces, and they erode into fines that keep the halo wide. That last trait matters for capture physics. More fines mean more cross-section per unit mass, which strengthens drag in any gaseous medium the body later meets. Two more steady facts keep the thinking honest. Refractory elements, including nickel, silicon, magnesium, and iron, set where and how dust condenses in a disk. Their ratios vary from place to place, but cluster around solar values in many solar system materials. And comets show diversity. Some are metal quiet in the gas, but rich in solid metals. Others display neutral metals in the coma, even at large distances from the sun. Diversity itself is not new. The pattern of this visitor's diversity is the question. Let the picture widen to function. If nickel is more easily liberated than iron from the grains now being heated, it hints at a dust mix with surface sites or coatings that favor nickel release. That could reflect formation under slightly different redox conditions, a history of mild processing that altered iron's habits, or a prevalence of minerals that bind iron more tightly. Each path points to an environment, not an accident. The environment could be a colder belt with limited shocks, or a region around a star with a different metallicity where condensation sequences diverged subtly from those we model for the sun. There is a second, quieter function that sits close to the seed idea. Refractory grains act as ballast in the nucleus and as grit in the envelope. Ballast sets spin behavior and how cracks hold. Grit seeds the flow with condensation nuclei and raises opacity in the forming envelope around a growing planet. If a captured body carries a dust mix that is unusually good at seeding clouds and regulating cooling, the early growth of a giant could be nudged in small, but persistent ways. Nickel does not make a planet. It nudges the weather at the right moment. Keep the technical bookkeeping compact. Metal lines in the optical and near ultraviolet rise and fade with solar distance and with vent exposure. Their flux often tracks the production of certain radicals, but not always. Iron-bound in coarser grains lags because larger grains take more energy to erode. Nickel from fine coatings or small clusters appears sooner. Polarization curves at multiple phase angles help separate geometry from composition. You do not need every number tonight. You need the pattern and its consequences. A second vivid image to settle the mind. Imagine snow shaken from a woven scarf. Fine, bright crystals drift easily. Heavier, darker flecks stay caught until the shake is stronger. If you watch from a distance, you might think the scarf holds only the bright kind. Closer in, you see both, but you remember which one left first. The role of distant origins returns now, gently. If the dust formed in a part of a disk where nickel-bearing compounds condensed more abundantly on grain surfaces, or if iron tended to hide in more durable faces, then a warming pass would favor nickel in the gas and leave iron conservative. The coma would whisper of that nursery without us ever seeing the parent star. The same would be true if the grains spent long ages in a cold, low radiation environment, preserving delicate coatings that dissolve quickly under our sun, but survive long enough to be measured. Skeptics ask whether instrumental bias or geometry could create the tilt. The careful answer is to look for persistence across instruments and nights, to compare with comets observed at similar phase angles, and to see whether iron wakes later as activity increases. If the imbalance closes as the body warms, the story is about layers. If it persists despite deeper heating, the story is about composition. Either way, the test leads to a physical interpretation, not a mood. There is a practical implication for capture mixed in this chemistry. Porous, metal-salted grains increase the coma's drag, both by area and by how they fragment. Gas drag acts on total cross-section, not just mass. A halo filled with fragile clusters that shed fines keeps the effective parachute open longer. In a young disk, that difference would mean a few more % of speed lost per pass. Small in an equation, decisive over a long curve. Two closing hard facts, then a soft edge to rest on. Metal abundances retrieved from spectra carry uncertainties, and coma composition is not always representative of bulk nucleus composition. Yet repeated detections that tilt in the same direction across geometry do reflect real surface inventories and processing paths. Polarimetry, though subtle, has mapped comet dust families for decades and does not require guesswork when its curves are clear. Those facts justify treating these solids as evidence rather than ornament. The open question to carry forward is modest and exact. Is the apparent nickel emphasis a surface weathering effect that will fade near the sun? Or is it a real signature of dust built under different rules in a different system? The answer decides whether this puzzle is a local accent or a passport stamp. Let the halo dim a little. and the lab lights hold steady. Metals ring, dust remembers, and the traveler's skin writes a small history in the air. The line between chemistry and dynamics narrows here. Refractories do not only name the nursery, they shape the break and the breath. Keep the thought close as we turn to size and shape, where capture stops being probable and becomes practical, warm, and sure. A fast ember slips into a velvet mist, not too small to be swept aside, not too large to punch through untouched. For a few careful minutes, scale decides fate, and the cosmos quietly keeps score. Think in shapes before numbers. A compact nucleus carries a shroud of gas and dust like a lantern ringed by moth light. That shroud makes the body bigger to the medium than its stone alone would allow. The medium in a young system is a broad sheet of gas threaded with pebbles. If the traveler's effective size is just right, every crossing trims a little speed without tearing the source apart. Two hard facts set the floor. Drag removes kinetic energy in proportion to exposed area, while inertia resists in proportion to mass. For bodies of similar density, area grows with size squared and mass with size cubed, so the ratio that matters scales roughly as 1 over size. A second fact follows naturally. Any active coma multiplies cross-section without adding much mass, so a modest nucleus wrapped in a big veil slows more efficiently than a bare rock of the same size. Here is the compact technical cluster held in one breath. The quantity engineers call the ballistic coefficient rises with density times size. Lower is easier to break. Gas disks at planet-forming ages are thin by Earth standards, yet their path lengths are immense, so tiny forces add up. A kilometer-scale nucleus with a coma thousands of kilometers wide can surrender a few percent of speed per deep graze. Repeat the graze, and a loose curve becomes a loop. Inside that loop, encounters get longer, and the break strengthens. Size matters, at the small end, for survival. Below a few hundred meters, rubble piles spin up quickly under sunlight or jets and can fragment. Small bodies also heat and cool fast, so violent venting can spall crusts. If a traveler unravels into fist-sized shards, cross-section rises for each shard, but the ensemble is soon ground to dust and entrained. Dust delivers chemistry, but not a ready-made core. Size also matters at the large end for capture. Tens of kilometers of stone have so much inertia that even a grand envelope cannot shave enough speed in a single pass, and repeated grazes are rare for bodies that do not bend easily. Survival is high, but adoption is unlikely. The sweet spot lies between, where survival and surrender meet. A vivid image to hold the principle. Imagine a maple leaf settling into slow syrup. A flake of ash floats aimless at the surface and never goes under. A river stone plunges and is gone. The leaf eases in and stays. How does the coma shift the window? Carbon dioxide that wakes early gives the traveler a working sail far from a star. Water thickens that sail near warmth. Porous dust makes the sail broader still for the same added mass. In effect, the cosmos lends a parachute to any nucleus that can keep breathing. A body that begins around a kilometer across, flares its envelope to thousands of kilometers, and maintains that breadth through rotation and refreeze cycles, will feel a break that a bare nucleus would never notice. Two more hard facts. Then back to pictures. Thermal skin depths on small bodies are shallow. A few centimeters to a few decimeters can separate the actively venting layer from a colder interior. That means modest heating can run a coma for long periods without hollowing the whole nucleus. And the stresses from venting scale with pressure and vent geometry, not simply with size. So well-placed cracks can act as nozzles that stabilize thrust on modest nuclei instead of ripping them open. Grounded speculation applies the window to our current traveler. If the nucleus sits somewhere around a half to a handful of kilometers across, it occupies the Goldilocks band for adoption. It is big enough to keep its shape through weeks of venting, and small enough that a swollen coma changes its fate in a gas disk. That same scale also makes dust lifting efficient without flooding the halo with boulders that collapse the envelope. Now link size to growth. Once residence begins, the effective reach of a captured body is set by its gravity and by how gas drag herds pebbles within that reach. A modest nucleus that has just crossed into membership carves a soft trough in the gas. Pebbles drift into that trough and collect where the newcomer's gravity can hold them. Size here sets a ladder. Too small and the rung is slippery. Large enough and each pebble stays to welcome the next. The climb toward a 10 Earth mass heart begins as geometry, not heroics. Keep the numbers clustered again. Think of a nucleus radius measured in kilometers, bulk density of roughly a gram per cubic centimeter to a few, coma radii in the thousands of kilometers, approach speeds in the tens of kilometers per second. A percent of speed shaved per deep pass is already meaningful on orbits measured in months. 3 or 4 such passes change outcomes. Inside the loop, gas cooling and dust settling decide how quickly the envelope trades brightness for weight. Dust properties braid back into size. Porous aggregates present extraordinary area for their mass, so the same nucleus feels a stronger break if its veil is fluffy. Fluffy halos also cool efficiently, preserving vent structures that meter thrust instead of exploding. The result is a stable, broad envelope around a nucleus that does not self-destruct. Stability converts potential drag into integrated loss. Integrated loss converts flybys into stays. Skeptics raise 2 good cautions. First, we see only the coma, not the stone, and models of size from brightness can mislead if the dust is unusual. Second, a generous envelope in our sun's light does not guarantee the same performance in a young disk where the gas is cooler and thicker. Both cautions are real. The answers are practical. Combine light curves, spin inferences, and gas production to bound the nucleus. Then run the same coma physics through the pressures and temperatures expected near 1 to 10 astronomical units in a disk. If the envelope remains broad and patient in those conditions, the window holds. There is a second vivid image worth keeping because it ties scale to feel. Picture a gloved palm lowered into a slow river. A pebble taps and darts away. A flat skipping stone slaps and lingers. The glove is the coma. The lingering is capture's first concession. At the edge of this discussion sits cohesion. Small nuclei with abundant volatiles can knit their surfaces each night as frost refreezes. That knitting, paradoxically, protects against catastrophic mass loss the next day. Larger nuclei self-gravitate strongly enough that even violent vents cannot lift big blocks easily. Between these regimes lies the band where nightly knitting and gentle gravity make a flexible shell. Vents stay narrow. Nozzles persist. The engine runs smoothly for weeks. Smooth engines keep parachutes open. What implications follow if this window is real? In the statistics from deep surveys, we should find that active interstellar bodies cluster in modest nucleus sizes more often than in extremes, because those are the ones that stay bright without shattering. Among the adopted worlds we eventually diagnose, the fraction that began on foreign hearts should correlate weakly with that same size band. The correlation will be messy, not crisp, because disks differ. Messy correlations are still useful. Two final hard facts to keep the table honest. Capture is a probability, not a promise, even for perfect sizes. Geometry matters. Angles matter. The disk must still be present, and coma physics is not free. Activity that multiplies drag also erodes the very stone that carries it. So lifetimes compete with opportunity. The window exists, but it is a moving window that slides with distance, age, and light. Set a gentle, open question at the edge of the frame. When we learn this traveler's true size and rotation more securely, will it sit inside the modest band that the capture math prefers? And if it does, what does that say about how many others like it pass unseen? Close, softly. Picture the ember again, not blazing, only steady, wrapped in its own weather. Scale gives it away to listen to the medium and to answer without breaking. For bodies like this, fate begins with a number that fits in the palm, like a pocket, warm and sure. A cold ember turns in sunlight, breathing a veil that catches your eye before your mind remembers the math. If a seed exists, it should look useful long before it looks grand. This one does. Watch how the pieces lock. Start with the face. It shows to heat. A carbon dioxide breath rises early, steady and pale. Then water joins and thickens the wake. The two-stage engine widens the envelope across a long span of light, which multiplies drag anywhere gas is present. The same glow that makes it easy to study makes it easier to slow. Function and visibility point in the same direction. Hold a compact cluster of numbers, then let them go. Gas disks thin in roughly 3 million years. A heavy heart, near 10, Earth masses, invites runaway in around 1 million. Carbon dioxide marks near 4.3 microns. Water hums, near 2.7 microns and beyond 5. Interstellar approach speeds sit in the tens of kilometers per second. Nucleus estimates life somewhere from a few tenths to a few kilometers. Enough scaffolding, nothing more. 2 hard facts anchor the case. First hard fact: the orbit is open and fast at infinity, which makes the traveler interstellar. Second hard fact: sustained activity includes carbon dioxide and water, confirmed independently, so the envelope is real, not a trick of geometry. From those 2 stones, we can step to the rest without slipping. Dust behavior strengthens the bridge. Polarimetry leans toward porous aggregates, grains that scatter sharply and present huge area for small mass. Porous dust cools efficiently, protects fragile chemistry in microshade, and breaks into fines that keep the veil broad. In capture physics, that is a gift. Gas drag acts on area. A fluffy halo is a bigger glove. Metals add a quiet signature. Nickel may speak more readily than iron in the gas at some stages, hinting at surface chemistry and coatings that part with nickel first. The tilt does not prove an origin by itself, but it matches a surface stitched from gentle winters and low compaction. A patient skin keeps vents narrow and nozzled, which steadies thrust and lengthens engine life. Size sits in the middle, like a hinge, too small, and the body frays into confetti. Too large, and it shrugs off drag. A nucleus around a kilometer, give or take, wrapped in a coma, thousands of kilometers across, lives in the Goldilocks window, where survival and surrender cooperate. It can keep shape through rotation, feed an envelope without blasting itself, and feel every brush with a young disk. A vivid image to hold the argument in one breath. Picture a leaf lantern drifting through a long hallway of slow air. It is not a brick, not a scrap. It is a shaped thing. Light meeting surface, surface meeting medium. The curve deepening almost imperceptibly with each pass. The grounded speculation is simple and testable. Put this traveler into a gas-rich disk, and it would lose a few % of speed per deep graze. More if the envelope is bright. After several grazes, the loop would close. Once resident, pebbles would stream into its hill sphere. Dust would feed opacity. Cooling would control collapse. And a giant's brief growth spurt would begin while there is still time left on the clock. Here's the pattern arranged as a profile, the way a field guide would print it. Profile marks. Early CO2 engine that maintains a wide veil at modest heat. Water transition that thickens, flow near the star. Porous. Polarization strong dust that multiplies cross-section and cools fast. Modest nucleus scale that balances endurance and break. Metal whisper that hints at gentle processing and stable vents. Interstellar kinematics that argue for foreign stock and a long cruise. Each line is ordinary. The set is not. It is exactly the collection you would hope for in a seed that must be seen, slowed, and then fed. Keep one last compact breath of mechanics, clustered once. Drag scales with area. Gravitational focusing increases path length in gas. Repetition turns tiny losses into capture. Opacity from dust sets how fast envelopes can cool. Less opacity after grains settle means faster collapse. Migration then moves the growing world, mixing the seed's cargo with the disk's pantry. No miracle parts, only familiar ones, rearranged. The second vivid image is tactile, to fix the feeling. Imagine a watchmaker catching a falling gear on a felt pad. The pad is the coma, the bench is the disk, the hand is gravity. The catch works because the gear has teeth and the felt has snap. Texture matters. For this traveler, texture is chemistry plus dust. The open question is precise and calm. How often does a disk meet a traveler with this specific combination of early CO2, porous fines, and modest nucleus? And what fraction of giants would that rate explain once surveys give us a population rather than a handful of letters? Soft ending for the night. Longer than usual because a chapter closes here. We followed breath into function, metals into memory, dust into drag, size into fate. Nothing asked for magic. Everything asked for time, contact, and light. If worlds sometimes begin this way, then the galaxy gardens without hurry, swapping sturdy cores the way rivers trade stones. Let the image linger, a small lantern turning in a long hall, the air itself keeping it, the room learning its shape. Ahead, the view widens beyond a single traveler to the roots that stitch systems together, like a pocket, warm and sure. The lantern from before keeps turning in the long hall, its veil catching the slow air. Now, the camera pulls back. The hall becomes a corridor of corridors, a web of lanes, traced not by footsteps, but by gravity, time, and the quiet exchange of stones between distant rooms. Picture interstellar space as an ocean without waves you can see. The currents are stellar motions through the galaxy. The winds are tidal nudges from spiral arms and passing stars. And the cargo is a billion small bodies set loose when young systems push them past escape. Most drift for ages. A few pass close to a new shore and find it willing. Two hard facts set the floor. Most stars are born in clusters, which means newborn systems begin life near many neighbors. Young stars commonly wear gas and dust disks for only a few million years. A window when captures and exchanges can actually matter. Those facts say the trading post is open early and it is crowded. Keep the compact numbers in one breath, then let them go. Typical star separations are a few light years. A protoplanetary disk persists around 3 million years. A star, like the Sun, circles the galaxy in about 200 million years. Relative drift speeds for small bodies are often tens of kilometers per second. Giant planets can eject trillions of planetesimals over their youth. Most of those will never meet a disk, but large numbers multiplied by long times make rare events routine. A vivid image to hold. Think of a dark archipelago under night, each island ringed by a pale reef of gas. From time to time, a tiny canoe glides from one reef's edge and, carried by a slow current, arrives at another. There's no flag on the canoe. There's only cargo and an invitation to stay. The mechanism that launches the canoes is simple. When giant planets form and migrate, they scatter smaller bodies. Some are flung inward and ground to dust. Some are stored in remote clouds. Some are given just enough energy to cross the line into interstellar space. That line is thin in velocity space and thick in outcome. Once a body is free, its path is set by the star's motion and the galaxy's pull. It becomes part of the background traffic. A second hard fact keeps the picture honest. Open clusters disperse in tens to hundreds of millions of years. But during that time, stars share similar velocities and pass one another at gentler relative speeds than random field stars. Gentler encounters last longer. Longer encounters increase the odds that a breathing object scraping a young disk will feel enough drag to bend into a loop. The Silk Road is not a single highway. It is a season when neighbors move together. Now the grounded speculation that follows without asking for anything theatrical. If exchange is easier inside birth clusters and still possible, though rarer, in the field, then a small fraction of systems will adopt foreign cores during their brief, gas-rich youth. Those adoptions would not be the only route to giants, but they would be a persistent supplement, a slow import trade layered onto local manufacture. There is another image that helps the hands remember. Imagine a cold fog bank crossing a valley of windbreaks. Loose leaves lift and settle from tree to tree, not because the trees call to them, but because the air carries them and the branches are there. Over a long distance, the valley changes its coat with no single gust to blame. Planetary systems, under this view, change their stock the same way. The network has structure. Spiral arm crossings stir velocities. Giant molecular clouds tug at orbits. The vertical oscillation of stars through the galactic plane modulates encounters with the distant reservoirs around each system. None of this is violent on the scale of a single comet. It is a slow choreography that modulates how often small bodies pass close enough to matter. Cluster the technical pieces in one place. Exchanges are favored when three ingredients align. Low relative speed, a breathing envelope that multiplies area, and a young disk within a few astronomical units of the pass. The first ingredient comes from shared birth motion or a fortunate geometry. The second comes from chemistry, such as carbon dioxide, waking early, and water joining later. The third comes from timing, because gas is short-lived. Multiply a tiny capture probability by the enormous number of travelers launched across billions of stars, and the integral delivers a real rate. Two more hard facts round the frame. We already see that interstellar objects exist, which means ejection is not rare. We also see that ringed and gapped disks are common around young stars, which means solids are constantly being herded where a captured core could feed. Those facts do not prove exchange is frequent. They do remove any need for special pleading. There is a gentle, dry smile available here. Planet formation diagrams often look like closed workshops. Doors and windows are drawn shut by habit. The network simply reminds us to sketch a window open. Material moves. It does not ask permission. What signatures would the transport network leave behind? On the supply side, the background density of interstellar objects would be higher than the few we notice. On the demand side, some exoplanet atmospheres would carry elemental or isotopic tilts that refuse to sit exactly on their stars' baselines, even after local gradients and migration are considered. On the spatial side, stars that formed in larger clusters might show a slightly higher fraction of giants with those tilts. The correlations would be soft, but soft is enough if the sample is large. A vivid scene to keep the idea tangible. See a slow caravan crossing a salt flat at dusk. Wagons leave one town with one balance of cargo and arrive in another with space to spare. The flat is the galactic disk. The wagons are small bodies. The towns are young systems still willing to barter. No heralds announce the trade. The ledger is written later, in the chemistry of the goods that changed hands. Skeptics ask the right questions. Do long cruises destroy volatile cargo? Do high relative speeds make almost every encounter meaningless? The cautious answers are measured. Many ices survive in the dark for millions of years when buried beneath even a few decimeters of crust. And while most passes are indeed too fast, the tale of slow encounters is not empty. It is there that a breathing veil and a broad disk do their work. Keep one compact paragraph for the geometry of mercy. Shared motion lowers relative speed. Gravitational focusing lengthens the interaction path. A coma, thousands of kilometers wide, increases the cross-section the gas can grip. Even a few percent of speed lost on a lucky pass is a down payment. The next pass in the same season can complete the capture. Seasons, not seconds, govern the network. What does this do to our sense of origin? It replaces a solitary workshop with a common market. A planet can still be mostly local. It can also carry a foreign centerpiece, a core that started under another sun and kept traveling until a young disk invited it to stay. The result is not a violation of the old rule book. It is a context that makes the rules less brittle. There is a final image worth holding as we step toward chemistry and life in the next movement. Picture a garden walled by hedges, and beyond the hedges, another garden, and beyond that, another. Birds cross without noticing the borders. Seeds drop where perches are kind. Over years, each garden grows a few surprises that did not start inside its fence. The surprises are not many. They are enough. 2 crisp facts to close the ledger for tonight. The galaxy holds hundreds of billions of stars, most of which likely made disks. Even if only a small fraction of those disks trade a single useful core during their brief youth, the absolute number of adopted beginnings would be large. And our own neighborhood has already shown us multiple interstellar visitors in a short span of time, which hints that the background traffic is richer than our small census suggests. A gentle question to carry forward. If the galaxy is a set of shared gardens, how much of what we call local heritage is actually borrowed? And how might we listen for that borrowing in the spectra of worlds we have yet to name? Let the lantern fade to a wider map. Lanes cross, caravans drift, and the quiet commerce of stones continues, whether we count them or not. In the next view, we consider what those caravans might carry besides weight, and why a seed can be more than a nucleus when a system is ready to grow, like a pocket, warm and sure. The caravan from the last scene keeps moving, its wagons dim and patient. Tonight, we look not only at stones, but at cargo. If a visitor can become a heart, can it also carry a pantry that matters? Imagine a small black flask, wrapped in frost, riding inside the veil of an interstellar traveler. Sunlight warms the glass just enough to let molecules seep into the halo. Dust around the flask shades them, catches them, and sends them onward like quiet notes on slow air. Two hard facts steady the thought. First, ices and dust in comets and meteorites are known to contain water, simple alcohols, nitriles, and amino acid precursors. They're chemistry, not rumor. Second, certain microbes and spores on or within rocks can endure vacuum, cold, and bursts of radiation for long stretches, especially when shielded by a few millimeters of material. Survival is not guaranteed, but it is not fiction. Keep the compact parameters in one breath so we can return to images. Organic films can hide on porous grains with surface areas that dwarf their mass. A thin layer of dust, a few millimeters thick, can cut ultraviolet doses by large factors. Meter-scale stones keep interiors cool during brief heating at entry. Exposure experiments show survivals measured in months or years, not minutes. Round the numbers, then let them go. Here is the vivid image that binds the parts. Think of a swarm of fine seeds drifting under a broad tarp. The tarp is dust, the seeds are small molecules, and the drift is the coma's slow wind. The tarp does not promise a harvest. It promises a delivery that reaches the field. Now, the grounded speculation, placed calmly in the light. If a young disk captures a breathing traveler, its first leaks will enrich the local gas with water and simple organics. As water vents deepen, larger mineral grains join the flow. Those grains carry catalytic surfaces that help small molecules climb one step toward complexity when they meet warm edges and cool shadows in the disk. In that setting, delivery and processing overlap. The pantry arrives as the kitchen opens. What about life itself? Sleeping and waiting. The careful answer is to keep the bar high and the tone plain. Dormant microbes might survive a cruise inside larger fragments, ejected from a system, protected from radiation and heat. Many would not. Some might. If even a few reach a young atmosphere or a sheltered niche without being sterilized, they could seed a chemistry that was already leaning in that direction. The difference is not binary. It is statistical, a small bias added to places that were close to ignition. Set the technique down once, then move away from it. When observers watch a visitor, like the one under our sun, they trace water production in the infrared and look for faint organic tracers in the violet and near infrared. They track dust polarization to learn whether grains are porous enough to shade and carry. They watch rotation to know whether vents, pulse, in ways that expose fresh material in cycles. If water and organics rise together and stay steady across geometry, the cargo is not a single crack. It is a stock. There is a quiet discipline to the timing. Early in a pass, carbon dioxide lifts fines that shelter fragile molecules. Closer in, water carries larger grains with clays and sulfides, minerals that turn sunlight and heat into slow reactions along their surfaces. Those reactions are not exotic. They are the simple couplings that build chains one link at a time when given patience, surfaces, and a solvent. A captured traveler would deliver patience, surfaces, and solvent into the same neighborhood. Two more hard facts to keep the mind trimmed. Re-entry heating is a skin effect for modest stones, so interiors can remain cool even when the outer rind flashes. And in our own system, impacts have moved rocks between worlds. Pieces of Mars lie in Earth's deserts and Antarctica. Transfer is not a story device. It is a thing that happens when gravity and time are given room. A small, dry smile belongs here. Cross-pollination is a plant word, and this is not botany. Yet the analogy holds where it should. Pollen does not build a tree from nothing. It nudges a living process that already knows what to do. In the sky, a seed that carries organics or hardy cells would not write biology alone. It would tip conditions that were nearly ready to write themselves. Let the numbers cluster again in one place. A young disk lasts around 3 million years. Capture asks for only a few % of speed lost per deep graze. Meter-scale fragments can shield interiors for years. Porous coma grains present large area and cast thick micro-shade. In that environment, transfer of water and organics is not rare. It is routine, measured in grams and kilograms, not in the heroic tons of cinema. Routine is enough when the processes are slow. What would count as a signature that the gentle cross-pollination actually happened? In an exoplanet atmosphere, a slight overabundance of certain nitrogen carriers relative to the stellar norm would be interesting, especially paired with heavier element enrichment that hints at dusty delivery. In a circumstellar disk, localized enhancements of simple organics near pressure traps could suggest repeated leaks. None of these would shout. They would whisper together. Skeptics ask whether cosmic rays erase everything over long cruises. The careful answer is that radiation eats from the outside in. Thin dust films weather quickly. Buried pockets last much longer. At the scale of microns, survival is a race. At the scale of centimeters to meters, the race slows. The coma itself is a moving shield, dense in the center, thin at the edges, always in motion. Chemistry inside that shield is never safe, but it is never helpless. A second vivid image to reset the scene. Picture a long table in a dim room. At one end, small bowls hold salt, sugar, oil, sour starters. At the other end sits a clean oven, already warm. A porter brings the bowls across the room, not in a rush, not in a parade, simply as part of the work of evening. The value is not in any single bowl. It is in their arrival before the heat fades. Bring the traveler back into frame. The current visitor likely cannot be a boat for living cells across the Gulf and into our air. The cruise is long, the light is unkind, and the chances are small. Its more probable cargo is simpler and more durable. Water to wet dust, nitriles to start chains, organics that like to stick to minerals and try combinations under weak heat. That is enough for our purpose. The seed idea requires chemical assistance, not a miracle stowaway. There is a practical inversion worth noting. We often think of comets and small bodies as late couriers that deliver after worlds are finished. The adoption path moves the delivery earlier, into the very hour that a planet is taking shape. Chemistry seeded then can be carried inward, buried in deeper layers, and held for long periods as quiet tracers of a beginning that mixed foreign stock into local grain. Keep a short ledger of tests that follow. Watch whether water and organic tracers scale with dust cross-section as the visitor brightens. Compare polarization curves to the persistence of faint organics, since fluffy grains should shelter more. Seek alignment between peak water output and the rain of larger grains that add catalytic surfaces. All of these are near the telescope, not beyond it. The open question to rest beside you is gentle and exact. How much of a world's later biology depends on this early overlap between delivery and formation, and how much arises no matter what, given time, rocks, and light. Close, softly. The caravan moves, whether we argue or not. Some wagons carry stones, some carry bowls, some carry nothing but the habit of travel. If a few bowls arrive on the right evening, a kitchen that was already warm may work a little faster and a little cleaner. That is all the claim needs to be, and it is already a generous one, like a pocket, warm and sure. Look at your hands, carbon and calcium that learned their shapes under other suns. Tonight, we trace how worlds inherit from many families, and why a single planet can hold the handwriting of a crowded galaxy. Picture a museum of sands. Under one lamp, grains from ancient red giants glitter with slow-forged carbon. Under another, silicates from supernova spray catch the eye. A curator mixes a pinch from each bowl and pours them into a single hourglass. The hourglass is a protoplanetary disk. Time, gravity, and light are the curator's tools. Two hard facts steady the floor. First, meteorites in our own collection contain pre-solar grains, tiny crystals older than the sun, with isotopic patterns that point back to different kinds of parent stars. Second, we have already seen multiple interstellar visitors drift through our neighborhood, which means other systems do in fact eject solid messengers into the galactic sea. Those facts do not require speculation. They are a record, a compact cluster of numbers, all in one breath, then back to quiet. A gas disk typically lasts about 3 million years. A star, like the Sun, orbits the galaxy in roughly 200 million years. Star clusters disperse over tens to hundreds of millions of years. During that crowded youth, typical separations are only a few light years, close enough for slow encounters to accumulate. Round the figures. Keep their shape. If this is the background, what does it mean for a single world? It means that any planet, even one assembled locally, is already a blend of many stellar histories that have been stirred into the interstellar medium. Hydrogen and helium arrive nearly everywhere. Oxygen, silicon, iron, carbon, and their companions come from a tapestry of sources. The disk is not a sealed pantry. It is a stew that remembers its ingredients if you know how to taste. A vivid image to keep close. Think of a violin made from boards cut from different slopes in the same forest. Each ring pattern, the echo of winters long ago. Under a bow, the instrument reveals those winters without words. Planets sing the same way. Their atmospheres, rocks, and dust resonate with the seasons of stars that never shared their sky. Where does a seed enter this story? Not as the whole song, but as a soloist that arrives with a recognizable accent. A captured core would carry the bulk chemistry and isotopic tendencies of a distant nursery in a concentrated piece, rather than as thin flavor mixed into the interstellar broth. When the disk adopts that core and begins to feed it, the local pantry adds volume, but the accent can remain audible in subtle ways. Two more hard facts help separate romance from work. Isotopic ratios are stubborn. Carbon 13 to carbon 12, oxygen 18 to oxygen 16, deuterium to hydrogen, nitrogen 15 to nitrogen 14, and others preserve memory of formation temperatures and pathways. And within our own system, different meteorite families show distinct isotopic neighborhoods. A reminder that even one disk can hold multiple reservoirs that do not mix instantly. These facts tell us that chemical heritage survives assembly. Grounded speculation follows. If a portion of giant planets formed around adopted cores, then a subset of those worlds should carry atmospheric metals and isotopic tilts that do not align neatly with the star they orbit. The shift would not be theatrical. It would be the kind of small, persistent mismatch that survives migration and weather. In rocky systems, the fingerprint might hide deeper, in mantle and crust, rather than in air, revealed only by rare samples or by indirect signatures of interior composition. Keep another compact moment of parameters, then set them down. A threshold core near 10 Earth masses invites runaway gas in roughly 1 million years. During that window, pebbles drift inward and deliver local dust. Gas brings the star's baseline. The seed's refractory heart contributes quietly to heavy elements and to noble gases if trapped early. The final blend is a weighted average, not a replacement of one heritage with another. Now return to the Museum of Sands and hold one specimen to the light. Precellar silicon carbide grains whisper of cool, carbon-rich giants. Tiny oxide grains whisper of oxygen-rich shells around other stars. Supernova bits carry excesses in specific isotopes that only shock-driven forges produce. None of these grains alone defines a planet. Together, they prove that the interstellar pantry is stocked by many kitchens, and that specks survive long enough to be found intact billions of years later inside stones that fell to Earth. Why dwell on this when our eye is on a single visitor, because the visitor makes the network concrete. If stones can cross, cores can too. If tiny crystals hold their identity through light years and eons, a kilometer-scale nucleus can certainly keep a statistical accent while it waits to be found. The seed pathway does not invent foreign heritage. It concentrates it into a part that the disk can grip and grow. A second vivid image, simpler, for the pocket. Imagine a quilt, sewn from cloth, traded over a century across a row of towns. Most squares came from the market down the street. A few came from caravans that only passed once. Those squares do not change the purpose of the quilt. They change its story. Two tests turn images into work. The first is comparative chemistry across planets around the same star. Shared starlight is a control. If one giant's metallicity and carbon to oxygen ratio lean away from the others under the same lamp, you ask why. The second is population statistics. If a measurable fraction of giants show the same class of tilt relative to their suns, and that class lines up with sizes and orbits that the seed method prefers, you have a branch on the family tree, not a single odd leaf. The shared heritage theme also threads inward to rocky worlds. Early in a disk, pressure traps and snow lines sort material into rings, each with its own temperature and chemistry. Mix in occasional foreign deliveries, and the rings become libraries, each filing system slightly different. When embryos sweep those shelves, they do not erase the ink on the pages, they compile. On Earth, we read echoes of that compilation in volatile budgets, in noble gas ratios, in oxygen isotopes that mark the dance with the moon's parent body. The details are local, the principle is general. You might worry that continued processing will bury every trace. Heating, differentiation, and atmosphere loss can blur lines. Yet some signals are stubborn. Noble gases resist chemistry. Heavy elements put bounds on interior mass. Isotopes with long half-lives tie today's rocks to ancient nucleosynthesis. Even when the song is muffled, the rhythm remains. A brief, rounded cluster of numbers as we close the ledger for tonight. Hundreds of billions of stars spread through a disk, roughly 100,000 light years wide. Most formed with disks. A typical system can eject uncountable small bodies over its youth, even if only a tiny fraction of systems ever adopt a foreign core while their gas lasts. The absolute number of adopted beginnings across the galaxy would be vast. The math does not strain. It sums quietly. A final image to carry forward. A child draws with crayons pulled from a mixed box. Some sticks were poured in one factory, some in another. A few are faded hand-me-downs from a friend. The picture is still of one house, under one sky. It is the box that tells a larger story. The open question is gentle and exact. When our catalogs of exoplanet atmospheres triple and our measurements of stellar baselines sharpen, will we see a recurring, explainable mismatch that points to adopted hearts? Or will the shared heritage of worlds prove to be so thoroughly blended that only rare cases betray their foreign square in the quilt? For now, keep the Museum of Sands in mind and the hourglass of a young disk turning under a new star. Shared heritage does not blur individuality. It gives it context. Worlds are local poems written in a language learned from many teachers, like a pocket, warm and sure. A map older than our star tilts under the frame. Above and below the thin, bright lane of the galaxy, a thicker, duskier stratum moves like worn stone steps. If a messenger comes from there, it carries an older accent. Hold the image while we set the floor. The Milky Way's disk is layered. The thin disk hosts most bright young stars and cold gas. The thick disk is older, puffed upward, its stars enriched in alpha elements from ancient supernovae and poor in metals compared with the sun. That difference is a history, not merely a label. Two hard facts. First, thick disk stars have larger vertical scale heights, roughly 1,000 parsecs, compared with a few hundred in the thin disk, and they show hotter kinematics, higher velocity dispersions, and a rotational lag of a few tens of kilometers per second relative to local circular motion. Second fact, their chemistry is alpha enhanced and typically metal poorer, with ages that often reach from 8 to 12 billion years. Those traits are a signature of the galaxy's quick, early forging and slower, later refinement. Now, the compact cluster of numbers, all at once. Think of a scale height near 1,000 parsecs for the thick disk, about 300 for the thin. Typical rotational lag for thick disk populations sits around 30 to 50 kilometers per second, with vertical dispersions of roughly 40 to 60. Metallicity often between minus 0.7 and minus 0.3 relative to solar, with alpha to iron ratios above solar, ages in round figures of order 10 billion years. The exact values vary with sample and place, but the silhouette is stable. Return to the traveler. A body ejected long ago from a thick disk system would have cruised under that older kinematic regime, not the colder swirl of the thin disk. If it kept drifting between the planes, its approach to our neighborhood could show a vertical component and a speed that feels slightly out of step with local traffic. The vector does not prove an origin by itself. It does offer a test, a vivid image to fix the idea. Imagine a smooth cobblestone, darker than the pavement, rolled downhill from an ancient road into a newer city. It fits beneath the wheel. It does not match the fresh bricks around it. The wheel does not care. A geologist would. Chemistry gives the geologist a handle. A thick disk nursery, poorer in metals, yet rich in oxygen and other alpha elements early on, would favor certain condensation sequences in its planet-forming dust. Refractories could tilt compositionally. Grain structures could lean more porous if early processing was gentle. And volatile inventories could partition differently as snow lines moved under a different metallicity and radiation field. If the traveler's dust is unusually fluffy and its refractory signatures hint at altered iron habits while nickel appears more readily, that may be the surface echo of a deep chemical history. Keep restraint where it belongs. A carbon dioxide forward coma is not owned by the thick disk. It is a function of how ices were laid down and buried. But in lower metallicity environments, with fewer heavy dust seeds, ice mantles can grow differently, and clathrate storage can bias which gases wake first. The result could be a two-stage engine that looks familiar, while its inventory leans subtly away from local norms. Kinematics and chemistry should be read together. Reconstruct the inbound radiant, transform to galactic U, V, and W components, and compare with local standard of rest. If the W component is notably large in magnitude and the V component lags, the path smells of an older population. Now compare coma chemistry, dust polarization curves, and any metal line balances with expectations for objects built under slightly metal poor, alpha, enhanced conditions. Neither set can carry the verdict alone. Together, they can draft a plausible ancestry. There is a grounded speculation worth making explicit. If 3I's inbound vector points to a high-latitude path with a modest rotational lag, and if its dust stays persistently porous, while metals in the gas tilt in a way that suggests altered iron release, then a thick disk heritage becomes the simplest story that fits both motion and skin. No singular number would demand that conclusion. The weight would come from coherence. A second image to carry in the pocket. See the galaxy as a layered sandstone cliff at dusk. The thin disk is a bright band where rivers still run. The thick disk is a deeper band, older, wind-carved, speaking in a lower register. A chip knocked from that older stratum would look ordinary in your hand until you held it to the lamp and saw the grains. What can be measured soon? The inbound vector and excess speed are basic geometry. Rotation period comes from jet pulses. CO2 and H2O production curves map storage and layering. Polarization across phase angles maps grain structure. Metal lines, if seen, track liberation pathways. Place those against models that compute dust growth and ice trapping for metal poor, alpha-enhanced disks. The exercise is not symbolic. It is a fit. Two more hard facts. Steady the ledger. Orbits of small bodies through the galaxy evolve under gentle tides and random nudges, but the broad kinematic imprint of a population can persist for billions of years. And chemistry at the surface of a nucleus is a palimpsest, altered by many summers, yet still capable of preserving original tendencies in bulk grain makeup and volatile reservoirs that were set by the birth disk. Skeptics raise the best cautions. A single approach vector can be misleading. Selection effects can bias which interstellar objects we detect. Surface chemistry can be reshaped by long cruises. The answer is the one we keep repeating. Look for persistence across independent signs. If only one line points up the cliff, the case is weak. If motion, dust, and gas all hum in the same older key, the case gets stronger. A compact, practical note for the seed idea. If thick disk systems were once especially fertile at ejecting planetesimals due to chaotic early dynamics, and if their small bodies formed with grain structures that favor broad comae, then thick disk migrants would be overrepresented among interstellar objects that both survive and present useful sails for capture in young thin disk systems. Exchange would then be not just across space, but across time. Let the notion of time travel shrink from poetry to lab work. We are not courting paradox, only inheritances. A body from the thick disk is a mineral sample from an era when the galaxy was still noisy with the first metals. When such a sample exhales under our sun, it writes old weather in new light. Keep the final image simple. A shard from a darker band turning in a younger room, whispering in chemistry and speed that it learned its habits elsewhere. If its vector and chemistry carry the old disk's accent, we will have heard a small voice from the galaxy's past. If not, the search continues, and the past will speak through another traveler, like a pocket, warm and sure. Curtains barely stir. Screens glow like small moons, and the mind loosens its grip. Imagine home not as a fence, but as a field that keeps widening each time you breathe and look up. Picture a child tracing constellations on a frosted window. The fingertip makes a new shape by linking stars that never touched. Our species has done the same with worlds. We drew boundaries around a system, named its parts, and decided that inside meant ours and outside meant theirs. Then the sky answered with travelers that do not care about our chalk lines. 2 hard facts straighten the compass. First, the rocks that fall to Earth carry pre-solar grains, solid witnesses older than the sun, each with isotopes that point back to long-vanished stars. Second, we have already logged multiple interstellar visitors passing through our neighborhood within a short slice of time. Proof that ejection and drift are not rare novelties, but normal traffic in the galaxy. Those facts are enough to loosen the old map. Keep the compact ledger in one breath, then let it go. A gas disk persists for about 3 million years. Star birth favors clusters where neighbors drift past within a few light years. Giant planets can expel vast populations of small bodies. Relative speeds usually prevent capture, but the long tail of gentle passages is never empty. Multiply small chances by long times and large numbers, and exchange becomes inevitable. A vivid image to hold the change in your hand. Think of an old city with secret courtyards, each garden walled and tended. Birds cross the walls without reading the bricks. Seeds hitch rides in feathers and fall where branches allow. In a few seasons, the quiet surprises become part of the garden's identity. Home did not shrink. It learned to include gifts. If we accept that planetary systems trade material, the word home shifts from a border to a practice. Home becomes the place where matter and light are currently arranged, aware that some of the matter learned its habits elsewhere. A gas giant may carry a foreign heart. A rocky world may bear volatiles from a neighbor's nursery. A comet may whisper in chemistry about winters under another star. The stories are not contradictions. They are the grammar of a shared language. 2 more hard facts keep the thought honest. Elemental and isotopic ratios in exoplanet atmospheres often diverge from simple copies of their stars. And in our own system, families of meteorites preserve reservoirs that never fully mixed during the disk's youth. Heritage survives assembly. It does not demand purity to be meaningful. Grounded speculation follows, plain and testable. If captured cores add to the supply of giants, then a subset of worlds should exhibit heavy element enrichments and isotopic tilts that resist explanation by local gradients alone. If interstellar seeds sometimes arrive with early carbon dioxide engines and porous dust, they will be easier to slow and adopt during the brief season when gas hangs in the air. These are not slogans. They are pointers for measurements already underway. This reframe softens our posture toward origin. We often ask for a single birthplace, a street address stamped on a planet's mantle. The sky keeps handing us passports. Heritage becomes plural. The young system is a studio, stocked with local clays and a few imported stones, where gravity and heat make something singular from mixed stock. The finished piece still belongs where it stands. It also carries the thumbprints of other hands. A second image, tactile and close. Imagine a bowl thrown on a wheel. The clay came from 2 riverbanks, and a small bag traded from a town upriver. The bowl is one shape, one use. When you hold it, you feel tiny specks that were not ground perfectly smooth. Those specks do not argue with the bowl. They give it texture. The shift in meaning has practical edges. When we say a planet is metal-rich, we learn to ask whether its wealth was mined locally or started with a seed. When we find water, we learn to ask whether it condensed from the star's breath or arrived in grains with a foreign accent. When we chart a migration track, we learn to ask whether the core that took that path had already traveled before it ever met the disk. There is a quiet kindness in this view. It lowers the temperature of our certainty. If heritage is shared, we do not need every system to solve its paradoxes alone. Some borrow time by adopting a ready-made heart. Some borrow chemistry by catching a traveler's breath. Some do both. The galaxy reads as a cooperative text rather than a collection of sealed notebooks. 2 small, steady facts return to the desk. The Milky Way holds hundreds of billions of stars, and a star like the Sun orbits the galaxy in roughly 200 million years, crossing spiral arms and drifting through changing neighborhoods. Over such spans, even modest exchange rates accumulate into real structure. We are already living inside the sum of many small trades. What does this do to the word home for us? It widens it without making it vague. Earth remains local, intimate, the place where liquid water holds, and biology edits itself patiently. Yet the carbon in your breath counted supernovae. The oxygen in your blood lists ancient forests of stars as references. The trace gases in the air whisper of comets that taught the young atmosphere how to keep a note. Home is here, and home is also a long conversation that started elsewhere. A grounded speculation adds one more step. If thick disk systems were especially enthusiastic ejectors early on, and if their small bodies formed with grain structures that favor broad comey, then some fraction of the seeds captured by younger, thinner disks could carry an older galactic accent. Planets built on such hearts would be time capsules with orbits, blending eras as easily as they blend elements. Now, a single gentle question, sized to carry into sleep. If our map of home must include the routes by which strangers became family, what new patience will we need in order to hear those roots in the spectra of the worlds we name next? Let the ending linger a little longer, because a movement closes here and the lamp is low. Think of a quilt pulled up to the chin, stitched from many squares. Some died in familiar rivers, some traded by a traveler who passed once and never returned. The warmth comes from the whole, not from the labels. The same is true for systems and for us. Home is the place where gifts keep arriving, where old grains find new patterns, and where a small, patient world breathes a wider story than the boundaries of its sky. In the next view, we step from philosophy back to tests, into appointments that the traveler will keep with Mars and with the sun, where light can answer what the night has allowed us to imagine, like a pocket, warm and sure. The quilt of shared gardens folds behind us, and the lens tightens. Home was widened. Now proof is required. In the red planet's neighborhood, a passing ember threads the dark. Instruments already cooled wait like watchful windows. If a seed is more than a metaphor, the next hours will give us numbers that either knit the new page into the rulebook or set it gently aside. Imagine Mars as a patient lighthouse and the traveler as a small boat slipping through the beam. The light does not stop the boat, it paints it. On the lighthouse decks, telescopes track the wake, counting colors and timing the flicker as the hull turns. The image is simple. The work is exact. Two hard facts set the floor. The geometry lines up for an early October pass, when the object and Mars draw near on the sky by tens of millions of kilometers. Close enough for good face angles, but far enough that only light, not dust, will reach the orbiters. Several spacecraft circle Mars with working cameras and spectrographs, so multiple eyes can watch the same event from different angles. That combination of timing and vantage is rare and useful. Keep the compact technical cluster in one breath, then let it go. The relevant gas fingerprints are water near 2.7 microns, carbon dioxide near 4.3 microns, carbon monoxide near 4.6 microns, and the violet CN band near 388 nanometers. Visible and near infrared imagers will map tail shape and jets against the changing sun angle. Ultraviolet spectrographs can sweep for CN and other fragments. High-resolution cameras can time the pulse of narrow jets to recover spin. One paragraph of parameters, then back to the window. Hold a vivid image for the setup. The planet is a dark red coin. The traveler is a sliver of pale breath. Between them hangs nothing you could touch, only the strict geometry of light. A jet turns like a watch hand. A camera blinks. A curve appears on a quiet screen. What does Mars give that Earth does not? Perspective. The angle of sun, comet, and observer controls which layers of the veil we see most strongly. From Mars, the face angle can place us almost sideways to the tail, which sharpens jets that would look flat from Earth. Also cadence. Orbital night and day let the same instrument return to the same target at regular intervals, so small changes become legible. And memory. We have watched a comet sweep past Mars before and learned that its dust and gas can touch a planet's environment. This pass is distant enough to be safe, close enough to be instructive. 2 more steady facts. Then we climb. Spectra gathered at multiple phase angles. Separate dust scattering from gas emission, which helps assign credit to the coma's brightness. And rotation survives distance. If a vent faces us every few hours, its pulse arrives in photometry even when the body is small. Together, those facts make an efficient plan. Watch the light. Measure the ratios. Time the rhythm. Here is the grounded speculation that matters. If the coma's early strength is truly carbon dioxide forward rather than a trick of distance and temperature, then even from Mars, the 4.3 micron band should remain lively while water strengthens more gradually. If dust is mostly porous fines, polarization and phase curves should lean toward the signatures we saw from Earth, only cleaner at a different angle. If both hold, the case for a broad, patient sail remains intact. Now, a compact moment on what cannot happen here to keep our feet. No spacecraft will fly through the coma. There will be no in situ sniffing. The distances involved forbid it. We will read light only, then compare that light to models of storage and release that already match comets in our own system. That is enough to push the seed idea forward or back without claiming more than the geometry allows. Return to the deck. Imagine one instrument tracing the rise of CN while another traces water and carbon dioxide in the infrared. The curves breathe with the nucleus spin. If the peaks align, one bundle of vents likely feeds several species. If they offset, storage is layered and different seams open at different temperatures. Either outcome turns romance into plumbing. 2 additional hard facts. Anchor the plumbing. Carbon dioxide can be stored as pure ice, in amorphous water ice, or in clathrates. Each has its own temperature response and its own hysteresis under repeated heating. Dust that is fluffy cools efficiently and helps preserve vent geometry by limiting local erosion. Those are lab truths as well as sky truths. They turn the curves into constraints on real materials. A practical precedent steadies the hand. When a comet skimmed Mars a decade ago, orbiters recorded bursts of gas and dust that briefly altered the planet's upper air. This encounter is gentler by orders of magnitude, which is useful. It lets us study the traveler as a source rather than the planet as a target. The lesson survives the change. Mars can be a laboratory lamp that shines from an odd angle at the right time. One more vivid image, tactile this time. Think of a glass blower, checking for bubbles by turning a lamp behind the work. Little voids flare and fade as the piece spins. The orbiters do the same with gas and dust pockets. Bubbles in glass are defects. Pockets in a seed are maps. If numbers are to earn their keep, they need a short ledger of expectations. Expect a modest carbon dioxide flux, even at cooler temperatures. A rising water curve nearer the sun. A dust brightness that scales with both. Expect a spin period revealed by repeating a pulses, perhaps on the order of hours. Expect small shifts in ratio with geometry. None of these requires optimism. All of them have been measured before in other travelers. The novelty is the combination. Skeptics ask for a falsifiable line, and they are right. Here is one. If the 4.3 micron signal slumps while water rises, and if dust behavior looks compact rather than porous across changing phase angles, the broad sail we have sketched shrinks. Capture physics would then have less leverage, and the seed profile would lose one of its strongest supports. The idea does not collapse, it trims. Another grounded speculation, cautious and useful. If the Mars vantage locks down a spin period, we can estimate how vents sweep the surface and how much thrust they supply. A small, persistent, non-gravitational acceleration consistent with CO2 and water jets would support the picture of a tuned engine rather than a chaotic exhalation. That, in turn, would matter for how long the parachute stays open in any gas disk. Keep a single, compact paragraph for the mechanics of reading thrust. Then let it go. Fit the path with gravity only. Measure the residuals. Compare the direction of the residuals with the derived spin axis and active latitudes. If the vectors agree, the jets are writing on the orbit. It is not drama, it is bookkeeping with starlight. The precedent of Mars also invites a look at dust sizes. High-res imaging from orbit can catch subtle changes in tail width and surface brightness that map to particle size distributions. If the tail narrows too quickly, grains are heavy and compact. If it stays broad under low force, fines dominate. Fines mean more cross-section, which means better braking. The line from pixel shape to capture math is straight. Let a final image ease the tone as the instrument clocks tick. The lighthouse windows do not shout. They blink with a patient rhythm. Out in the beam, the boat turns and breathes. Between them are only angles and time. Yet those two things can decide whether an idea moves from perhaps to likely. A gentle open question to carry forward. When the curves are overplotted and the pulses aligned, will the Mars angle reveal an engine and a sail as wide as we hoped? Or will it show a quieter traveler whose breath cannot help a young disk keep it? Close, lightly. The red coin turns. The small boat slides through the beam. Somewhere in the telemetry, a signature gathers. It will either lengthen the new page we penciled into the rule book or sketch a smaller margin. Either way, the night stays generous to those who let light do the talking, like a pocket, warm and sure. Heat gathers like a held breath. The traveler angles inward, and the quiet veil we have watched for weeks tightens into weather. If the seed keeps its shape here, the rest of the story can afford patience. Imagine a small, dark kiln turning toward a white furnace. Hairline seams glow. Old frost thins. Gas thrust begins to ride on the path instead of only on the halo. What looked like a soft exhalation becomes an engine that the orbit can feel. 2 hard facts. First, set down plainly. Perihelion is the closest approach to the sun, the hour of peak heating for a single pass. In most small icy bodies, water becomes the main driver near this point, while carbon dioxide either continues from deeper pockets or retreats as shallow stores empty. Those facts do not ask for belief. They have been measured in many travelers. Keep the compact parameters in one breath, then let them go. Thermal skin depth on a small nucleus is measured in centimeters to decimeters. Rotation periods are often hours. Non-gravitational accelerations from jets can shift the orbit measurably when activity is strong. Dust production tends to increase as water flow rises, with grains ranging from submicron powder to millimeter pebbles. Enough scaffolding. Back to the lamp. Hold a vivid image for the transition itself. Picture a watch spring catching firelight as it turns bright, dim, bright, dim. Each bright face is a vent aimed at the sun. The dim is the same vent turned away, cooling and refreezing. The period reveals the clockwork, and the clockwork reveals where strain will find a purchase. This is where chemistry and structure negotiate a truce. If the crust has been slowly knitted each night by refreezing carbon dioxide, the new heat will test the stitches. Water vents will either widen cleanly and settle into steady nozzles, or they will excavate flaking pits that feed erratic outbursts. The outcome decides whether the veil becomes a broad sail or a torn flag. The difference is not poetry. It is cross-section over time, and cross-section over time is capture's currency. A second hard fact: quiet but decisive. The strongest water bands, near 2.7 microns and beyond 5 microns, rise steeply when the sun angle is favorable and the surface warms. If production follows rotation with a stable period, vents are organized. If production wanders, the surface is breaking. Either way, the light writes a diagnosis, while the heat does its work. Here is the grounded speculation that matters for our seed path. If the traveler has truly carried a carbon dioxide first engine with a patient, porous veil, then the water phase will thicken the envelope without tearing the shell. Dust will become heavier on average, but fines will still dominate the area. The sail will stay wide, the effective parachute intact. Capture physics in a young disk would gain, not lose, leverage from this moment. Keep a compact cluster of failure modes in one place so they do not crowd us. Outbursts can shed slabs, exposing fresh ice and jolting the spin. Spin-up can drive mass loss if cohesion is low. Cracks can link into fractures that rearrange vents. None of these is shameful. They're ordinary ways that small bodies adapt to stress. For our question, what matters is persistence. A seed cannot help a disk if it shreds itself into confetti. Dust behavior now becomes a second barometer. If polarization curves continue to favor porous aggregates, even as water takes over, the grains are still fluffy, still high area, still kind to drag. If the curve collapses toward compact scattering, the veil is filling with heavier fragments that narrow the sail. A narrowing sail is not a failure of nature. It is a change of function, one that capture math must respect. Think again in images so the hands can feel the difference. The kiln with steady seams is a lamp that brightens and holds. The kiln with flaking pits is a sparkler, brilliant and brief. For a parachute, steady always wins. Two more steady facts, then a brief technical breath. Non-gravitational accelerations, small but persistent, point roughly along the bisector of the main jet activity when averaged over spins. Shape models can be inferred from light curves if the rotation is not tumbling. When those two are combined, we learn not only that jets exist, but how they push. That pushing is a preview of how a coma would couple to a disk's gas in a different life. The compact breath. Fit the trajectory without jets and read the residuals. Recover the spin axis from the facing of jets. Compare the residual direction to the spin geometry. Agreement turns a nice image into a working trust map. Now put the notebook away and return to the furnace. What does the interior reveal at peak heat? Layering. If carbon dioxide lives in clathrates or in amorphous ice that releases trapped molecules when it crystallizes, the timing of secondary carbon dioxide peaks will lag water in a pattern that betrays depth. If those peaks are absent, the pantry is thin and the shell is doing most of the talking. Either outcome is useful. A thin pantry tells us the traveler has weathered many summers and still breathes. A deep pantry tells us that broad comae are not a trick of surface varnish, but an inventory choice made long ago. There is a narrow sweetness to this moment that deserves a quiet smile. We are watching a small object argue with a star about how to keep its shape. The star has all the leverage. The object has all the tricks. Vents act like valves. Dust like a wick. Rotation like a metronome that distributes pain. Now, a practical note about color and size. Coma color, slopes that redden with distance and then flatten near perihelion, often signal a rising load of larger dust. If the slope stays red, while polarization remains high, fines still dominate area. If both shift toward neutral and low, the veil is compacting. That shift is a useful index for the sail's health. At the same time, tail width, mapped against solar radiation pressure, sets particle sizes cleanly enough to catch day-to-day changes. Small changes are the evidence we need. Large changes are the drama we can do without. Grounded speculation extends one more step. If water-driven vents remain confined and behave like nozzles, the net torques can alter spin period slightly across the weeks around perihelion. A small lengthening or shortening, measured honestly with uncertainties, would confirm that thrust is organized. Organized thrust is the quiet partner of a durable sail. Both are good news for the capture idea. The vivid image that binds the chapter arrives near the exact turn. Imagine the kiln, now face on to the furnace. The bright vein wakes. A white breath thickens. You can see in your mind a thin ribbon of material cast sidelong, then another, matched to the turning. The ribbon does not tear the kiln. It steadies it. The halo grows and smooths. Skeptics ask the fairest question of the night. What would count as a strike against the seed profile here? The answer has sharp edges. If perihelion brings a collapse of the 4.3 micron line, while water rises, and if dust signatures swing toward compact grains with low polarization quickly, and if rotation signals lose coherence, then the wide, patient sail we have sketched is probably a temporary facade. Capture would still be possible, but the leverage we hoped for would be smaller and the window narrower. Two closing hard facts to keep the ledger honest. Perihelion changes are not uniform from pass to pass, even in bound comets, and we have only this one pass. And coma composition is a surface-weighted sample. It hints at interior make, but it is not a biopsy. Those facts do not weaken what we learn. They frame it, set a gentle, open question at the edge of the frame. After the furnace, what remains? A veil that learned to be stronger, or a skin that spent itself for one bright turn. The answer will decide whether this traveler is only a guest in sunlight or a credible seed in a young, gaseous room. Close, lightly. The heat will crest and ease. The kiln will cool, knitting seams in the dark again. Whatever the verdict, the orbit will ride it softly into the next arc of space. We will read what the light allows and carry the rest as a patient thought, like a pocket, warm and sure. The furnace is behind us. Now the census begins. On a desert mountain, a giant eye will blink all night, catching every moving fleck. If seeds exist, statistics will summon them like constellations emerging from noise. Picture a slate-colored dome under thin air. Sunset drains, the shutters part, and an 8-meter mirror starts a patient heartbeat of exposures. Each beat writes a fresh map of the sky. The next beat subtracts the last and leaves the differences standing. Stars cancel. Ghosts cancel. Anything that moved remains. Two hard facts steady the promise. First, the survey will scan most of the accessible sky every few nights for about 10 years, returning to each field with a pair of back-to-back snapshots that fix motion as well as brightness. Second, an alert stream will flow in near real time, flagging new movers within a minute so telescopes around the world can slew and listen while the trail is still warm. Those facts make rarity workable. They turn luck into cadence. Keep the compact technical cluster in one breath and then let it go. Single visit images reach roughly magnitude 25, enough to net small bodies far from the sun. The field of view is about 10 square degrees per exposure, which means huge swaths of sky with each blink. Visit pairs separated by about half an hour give sky plane velocities. Over 3 to 4 nights, repeated visits yield tracks and preliminary orbits. Hyperbolic fits fall out naturally. Trailing losses are corrected by software tuned to catch streaked sources. One paragraph of gears is enough. Back to the night. A vivid image for what this means. Think of a fresh snowfall, seen from a porch light. Stand still for a minute, and every falling flake appears alone. Wait, and patterns emerge. The same drifts form in the same corners. The sky has habits. The survey's gift is to keep waiting long enough for habit to become evidence. The first target is simple. Turn a handful of interstellar visitors into a population. With a population, you can sketch a size distribution. You can plot speeds at infinity. You can compare the rate of discovery at large solar distances with the rate near the sun and infer how often bodies wake early. If many wake with carbon dioxide while still far out, more of them are visible sooner, and more of them can be measured before their geometry becomes difficult. That is not a slogan. It is a bias you can count. Here's the grounded speculation that follows from that bias. If carbon dioxide first travelers are common, detection will pile up at longer distances with a color and brightness behavior that betrays early coma. Those will become the best candidates for the kind of broad sails that capture math prefers. If they are rare, discoverable interstellar objects will cluster closer in, and the seed idea must lean more on the occasional geometry that favors drag, even without an early veil. Either way, the census selects, and selection speaks. Two more hard facts add backbone to the plan. A survey like this does not hold objects for itself. It publishes alerts quickly enough that a global network can do spectroscopy, polarimetry, and precision astrometry while the light curve is still growing. And moving object pipelines are mature. They were built for asteroids, but adapt well to hyperbolic tracks, provided the cadence holds. Those facts turn a single mountain into a distributed instrument. You can hear the sleepy physicist voice. Keep the stakes plain. Population breaks stubborn stories. With a few cases, arguments become anecdotes. With hundreds, argument becomes atmosphere. You breathe the histogram and its peaks and valleys. You stop guessing which properties matter. The bar chart does the talking. Let the image tighten onto a screen in a warm control room. New frames arrive like tide. Each one is the same view with one night of parallax. Difference images lift small needles of light that moved. Software chains the needles. Humans sanity check the chains. A point becomes a path. The path whispers about speed and distance, then decides whether gravity can hold it or not. Some paths loop. Some paths do not. The ones that do not are our letters from away. A compact list of what those letters can tell us, beyond the simple count. Skyplane speed and brightness. Evolution. Give size estimates and hints about activity. Color, slopes. Tell you about dust in broad strokes. If a candidate is bright enough. Polarimetry from modest telescopes can flag fluffy grains with a distinctive phase curve. The objects with early coma will then form a subsample labeled not by romance, but by optics. We will learn whether that subsample is large or small. Consider the beachcomber logic that follows. If early comae correlate with higher detection distances and with velocities at infinity that cluster in a certain range, we will infer formation environments that favor those two states together. If early comae have no preferred speed, the chemistry is not a product of birthplace, but of later processing. Statistics, not adjectives, will sort it out. The survey's cadence has another quiet boon. It'll catch outbursts and quenching in real time, revealing how vents evolve in a population rather than in one object. Do most travelers stutter or sing? Do spin periods cluster? Do colors drift in the same direction near the same distances? Each small pattern turns what we did for weeks with one traveler into a repeatable checklist. 2 additional hard facts keep the ledger honest. The main camera works in optical bands, so it will not read carbon dioxide directly. It will, however, catch the dust that carbon dioxide lifts at large distances where water sleeps, and the survey's uniform cadence avoids one of the oldest traps in small bodywork: the temptation to draw trends from irregular attention. When every field gets the same gaze and the same rhythm, absence means something. A second vivid image to keep the mind steady. Think of a lighthouse that paints the whole horizon every few nights. Not for ships, but for driftwood. Each time the beam passes, sticks that moved change the highlight on their wet edges. The beam does not know origin stories. It knows movement. That is enough. A practical aside turns the beam into inference. Fit hyperbolic solutions for the new movers. The distribution of excess speeds at infinity is the fossil of ejection energetics in many distant systems. A narrow distribution hints at common launch mechanisms. A broad one implies variety. If a narrow subset coincides with early comet, you have a group worth naming and testing. Keep the technical parameters clustered once more, so they remain gentle. Expect many alerts per night, only a small fraction of which are interstellar. Expect machine filters to miss and to over-include at first. Expect follow-up to be the bottleneck. Expect the community to adapt within a season. These expectations are not cynical. They are how large surveys grow muscles. Now, bring our seed idea back, not as a claim, but as a beneficiary. If the census reveals a family of early waking travelers with porous dust signatures and modest sizes, capture physics gains a supply. The question shifts from can it happen to how often. Then the same statistics that found the family can constrain the rate of adoption by comparing discovery numbers to the fraction with chemistries that multiply drag. Skeptics should have a clean line to pull. If, after years of scanning, interstellar discoveries remain rare and dominated by bare stones, seen only near the sun, the seed pathway must retreat to unlikely coincidence. If, instead, they are frequent enough and often wearing wide veils early, the pathway moves from romance to resource. Either conclusion is a win. The rulebook grows either way. There is a last image worth keeping as the desert wind rises and the dome rotates. Think of a creek filled with sunlit moats. At first, they look random. Then you see the same curls and eddies guiding them past the same stones. The field we are about to read is not random. It is patterned by formation, by ejection, by light. We have simply lacked the patience to watch the curls repeat. 2 closing hard facts, and then rest. 10 years of uniform cadence builds a library strong enough to survive our biases, and a shared alert stream makes the library public as it is written. So many hands can translate at once. That is how rare ideas become ordinary work. Soon the night will fill with small proofs drawn from motion. Counts will thicken into curves, and curves will turn into a verdict. Will the patterns show a family of early waking travelers that a young disk could keep? Or will the sky remain a scatter of strangers passing unclaimed, like a pocket, warm and sure? Night tightens around the subject. It is time to weigh the quiet possibilities. Nature offers 3 simple stories: a normal comet, a useful seed, a crafted artifact. We tip the scales with light, not desire. Lay the baseline first. 2 hard facts stand like posts in the dark. The path is hyperbolic, with excess speed, so the traveler is interstellar. Spectra show carbon dioxide and water, so the veil is chemistry, not glare. Everything else is a question of fit. Picture a jeweler's bench with 3 small stones and a scale. The first stone is ordinary, unpolished, cool to the touch, comet. The second stone is the same mineral, but cut so its faces catch the light, seed. The third is glass, maybe carved, artifact. The trick is not to reach. The trick is to weigh comet first, because the simplest story deserves the first look. In this telling, the object is a volatile, rich body, ejected from another system, now warming under our sun. Carbon dioxide wakes early. Water joins near heat. Dust lifts across a wide range of sizes. Polarization suggests porous grains built in gentle regimes. Non-gravitational nudges track with rotating jets. The signatures line up with physics we already use to read comets at home. If the Mars vantage and the weeks around closest approach keep those curves steady, comet earns a heavy place on the scale. This story's numbers can be kept in one breath. Nucleus scale of order, a kilometer. Coma, thousands of kilometers wide. Gas lines near 2.7 and 4.3 microns, breathing with a spin of hours. Dust phase curves that favor fluffy aggregates at several viewing angles. No extra machinery required. Only ice, rock, sunlight, and rotation. Now, the second stone. Same ingredients, different consequence. Seed. In this telling, the cometary behavior we see is not just decoration, but function. A carbon dioxide first engine widens the envelope early. Water thickens the sail near heat. Porous fines multiply cross-section. In a young gas disk, that broad veil becomes a break. A few percent of speed lost per deep graze, repeated, closes a loop. Once resident, pebbles drift inward. Opacity falls as grains settle. Cooling accelerates, and runaway gas accretion begins while the disk still lives. The traveler is not a planet. It is a ready-made core that can become one when conditions allow. What turns seed from flourish to wait is not this single pass, but coherence. The profile we have built: early carbon dioxide, persistent fines, modest nucleus, organized jets, maps directly onto the capture math. If Mars confirms a strong carbon dioxide line at cooler temperatures, and if perihelion keeps the veil broad without shredding, the stone-marked seed grows heavier. It is still a conditional label. It becomes a useful one. Then the third stone, the uncomfortable glass, artifact. To stand here, the evidence would need to veer from natural habits. We would look for geometry that refuses randomness in a way chemistry cannot produce. Mirror-flat, specular glints, accelerations that do not point where vents do, narrow-band signals tied to rotation, surfaces that hold unnaturally constant albedo despite dusting. None of those has been reported. Outgassing explains small orbital residuals elsewhere. The halo looks like gas and dust, not exhaust. The burden for artifact is high because the cosmos already offers common tools for what we see. A vivid image to hold the distinction. Set the three stones under a lamp and spin them. The comet scatters with a soft shimmer that thickens near heat. The seed scatters the same way, but sits inside a sketch that fits a capture problem. The artifact would flash on a schedule no geology keeps. The room is bright enough now that a flash would be hard to hide. Keep the skeptical ledger tight. Could selection biases make a normal comet look like a seed? Yes, we favor bright, early waking visitors. That is why a population from wide surveys matters. Could layered ices mimic tuned engines? Yes, and nature often tunes without intent. That is why we ask for persistent patterns across geometry and time. Could subtle systematics hide an engineered signature? Perhaps, but then the artifice would be indistinguishable from geology, which empties the claim of use. Cluster the technical tests all at once. From Mars, phase angle, leverage on jets, spin, and band ratios. Near the Sun, persistence or collapse of the 4.3 micron line, dust polarization under stress, and tail width diagnostics for grain sizes. In orbit fitting, residual vectors aligned with jet geometry rather than arbitrary thrust. In population work, whether future interstellar discoveries often wake with carbon dioxide far from stars, and whether porous dust is common in that subset. These are the pages the sky is already writing. We do not need new ink. A grounded speculation that keeps faith with physics. If the seed hypothesis is right, even for a minority of giants, we should find exoplanet atmospheres with heavy element enrichments and isotopic tilts that refuse to sit neatly on their stars' baselines, clustered in ways that match sizes and orbits where capture is easiest. If we do not find such patterns after the census grows, seed recedes to a rare path. The comet stone stays, the artifact stone stays light. Numbers for sleep, kept round and brief. Disk lifetimes, about 3 million years. Runaway gas, around 1 million, when a core nears 10 Earth masses. Nucleus scale, near 1 kilometer. Coma scale, in thousands. Excess speed at infinity in tens of kilometers per second. 3 stones on 1 scale. Only one needs more weight than romance. Hold a single vivid picture As the weighing ends, a hand lifts each stone in turn. The ordinary one sits heavy with the comfort of precedent. The cut one balances slightly heavier than its size because edges catch light and friction. The glass one, smooth and convincing in certain angles, stays light when the fingers know texture. Close with two steady facts that survive any verdict. Interstellar objects are real and varied. Chemistry and dust, read with care, will sort families we cannot yet see. Those are enough to make the next measurements worth the patience. And a gentle, open question, small enough to carry into the dark, when the last curves from Mars and the Sun are stacked beside the first histograms from the new survey. Will the cut stone keep its extra gram, or will the scale return to ordinary weight with a quiet click, like a pocket, warm and sure? The night leans closer, and the question finally stands without a handrail. Are we shaped only by the fire of our own sun, or also by travelers that cross the dark with quiet purpose written in physics alone? Picture a tide line at dawn, thin ripples stitched with shells from different coves. Each wave sorts, gathers, retreats, then returns with a slightly new grammar. A planetary system is the same kind of shoreline. Time is the tide. Small bodies are the shells. The pattern is patient. Two hard facts steady the thought. Gas-rich disks do not wait. They thin in a few million years. So any workable path to giants must move quickly. Interstellar traffic is real. We have watched multiple visitors on open orbits, which means other suns do cast stones into the shared sea. These are not slogans, they're measurements. Keep the compact ledger in one breath, then let it go. A core near 10 Earth masses invites runaway gas in roughly 1,000,000 years. Approach speeds at infinity are often tens of kilometers per second. Early carbon dioxide wakes at lower heat than water. Porous dust multiplies cross-section without much weight. Large surveys will soon turn anecdotes into curves. Enough numbers for the pocket. Here's the quiet compromise that follows. We are children of our star because its light set the climate of the disk and wrote the temperature map that sorted ices and rocks. We may also be children of seeds between stars because a fraction of worlds likely began when a ready-made core was kept by gas and fed by pebbles while the clock was still kind. The two stories do not compete. They complete. A vivid image for the hand. Think of a potter's wheel and a small, polished stone pressed into the clay as it spins. The wheel belongs to the studio, the clay to the river nearby, the spin to the foot that turns it. The stone is foreign, yet the final bowl is local and whole. What would seal this view is not a single elegant case, but a population that hums the same low note. Worlds whose metallicities sit above their stars. Noble gases that hint at colder starts. Isotopes that lean away from local lines. Interstellar visitors that wake early and wear wide veils far from heat. Add those up, and a minority report becomes a paragraph in the rulebook. The grounded speculation stays modest. If adopted cores explain even a slice of the timing paradox, then some giants we have already named are cousins to strangers whose names we will never learn. Their heritage will be identifiable not by stories, but by ratios, by lines in the infrared, by dust that bears the memory of a nursery we cannot see. No ceremony required, only patience. A gentle question remains, light enough to carry with you. When our catalogs thicken and the curves from many nights are finally stacked, will we hear that quiet minority singing in tune? Or will the shoreline prove so well mixed that only a few shells still tell where they began? And now, a soft, open edge to close the section. The answer may be plural. We may be local clay turned under local hands. And we may hold a seed set traveling long ago, caught by a young wind and kept by a patient tide. The sky is wide enough for both truths, and the work ahead is only to listen carefully and to name what the light allows, like a pocket, warm and sure. Let the room dim. Breathe the simple rhythm that instruments keep when they sleep. A hum under the floor, a clock that does not hurry. Think of a small body, far away, cooling, knitting a thin frost along seams that brightened for an hour. Think of Mars returning to ordinary red, and the sun setting its long arc toward winter without comment. We hold a question because the night is kind to questions. It lets them float without verdict. Children of a single star, or also of seeds between them. The difference is less about pride than about kinship. If exchange is part of the way the galaxy makes worlds, then the word home grows a softer edge. Home becomes the place where gifts arrive and where we learn to recognize them without demanding that they carry our name. Let numbers fade to round shapes. A few million years for gas, a million for a giant to rise. A handful of travelers in a decade that hint at a background we have barely begun to count. These are not alarms. They are lengths of music that repeat until you know the tune. Perhaps, when surveys settle into their cadence, we will watch a family of early waking drifters appear, pale comet, drawing slow lines between stars. Perhaps we will find only a scatter of quiet stones. Either way, the sea remains. Either way, the craft endures. We place one measured curve beside another, and the story writes itself in lowercase, steady and clear. If you are still awake, let the shoreline return. Small waves climb and slide. The wet sand keeps a few prints until the next pass. Somewhere in that pattern is a bowl turning on a wheel, a lantern breathing in a long hall, a seed that is only a stone until a medium gives it room. Rest with this. You belong to one star without remainder, and you also belong to a larger field that shared its tools. There's comfort in both. The world outside is quiet now. Keep a little of that quiet with you. Let your breath slow. Let the window fade to gray, and let the cosmos close its hand around you like a pocket, warm and sure.